हेलो, स्ट्रीमिंग स्टार्ट किया ना एक्चुअली? हेलो, बढ़िया. या सो गुड इवनिंग ऑल ऑफ यू. कैसे आप सब लोग? एक्चुअली बहुत दिन के बाद मिलने का मौका आया एंड आई थिंक लास्ट टाइम जब रामानंद बंसल सर में बाक इंटरव्यू के लिए एक सेशन लिया उस टाइम पे हम मिला था एंड दिस इज गोइंग टू बी अ सेशन ऑफ ISRO PYQs ऑन एप्लीकेशंस ऑफ थर्मोडायनामिक्स. एंड हमको पता है कि हर एग्जाम के लिए PYQs बहुत इंपॉर्टेंट है एंड ISRO एक ऐसा एग्जाम था जिन लोगों का सपना है कि साइंटिस्ट बनना है, सो उन लोगों को दिस ISRO इज लाइक वेरी गोल्डन अपॉर्चुनिटी फॉर यू गाइस. ओके, सो बेसिकली इस ISRO PYQ सेशन में इस 7th लेक्चर था इस एप्लीकेशंस ऑफ थर्मोडायनामिक्स. बेसिकली लास्ट टाइम जब गेट से पहले जब हमने रिवीजन 2 क्वेश्चंस एंड बोथ सेशंस किया उस टाइम पे भी मैंने अपनी थर्मोडायनामिक्स एंड कुछ फ्लूइड मैकेनिक्स का सेशंस भी किया था, आप लोगों को पता है. एंड यू नो दिस सेशन इज लाइक ए वेरी गुड knowledgeable session, is going to be a very good knowledgeable session for all the pass out students, okay, and also people who are in the final year and जिन लोगों का ISRO का एप्लीकेशन बनने का मौका आए थे उन सभी लोगों के लिए ये सेशन बहुत अच्छा सेशन था एक्चुअली. ओके, क्योंकि इस सेशन में हम PYQ सॉल्व करते हैं एंड ऑल्सो PYQs के साथ हम बहुत कुछ अच्छे पॉइंट्स भी डिस्कस करते हैं ISRO एग्जाम के लिए, उसके बाद इंटरव्यू अपीयरेंस के लिए, ये सारी चीजों के लिए. ठीक है, सो लेट अस नाउ फोकस ऑन दिस क्वेश्चंस बेसिकली. एंड बीच में मैंने कुछ पेड बैच से कुछ स्लाइड्स लेके भी आया था क्योंकि उस टॉपिक से हर चीज यू नो एवरी टाइम देयर कम्स ए क्वेश्चन, यू नो एवरी ईयर देयर इज ISRO इक्विपमेंट, देन दैट्स व्हाई this session is going to be very you know knowledgeable session for you guys. Okay, JE 2025, please guide me, is there any scope in engineering? Yes, definitely engineering mein always you have a lot of scope actually here. Okay, so let us start with this question. In a PV diagram of a steady flow compressor, the intercooling can be represented as. So intercooling क्यों करते हैं पहले? Okay, so what is the necessity to do intercooling in any compressor? So आप लोगों को पता है कि normally compressors अगर कुछ gases या A से रन हुआ तो PV is equal to RT, normally the ideal gas equation. So जब हम कंप्रेस करते हैं उस टाइम पे एयर का टेम्परेचर बढ़ेगा, ये सबको पता है. मान लो कि ये PV डायग्राम था. ओके, सो दिस इज द PV डायग्राम एंड अगर ये PV डायग्राम है तो मान लो कि एक कंप्रेसर ने एक लो प्रेशर से लेके एक हाई प्रेशर तक कंप्रेशन कर रहे हैं. सो उस टाइम पे क्या होता है, अगर आप सिंगल स्टेज में कंप्रेशन किया तो मान लो कि something like this. Let us suppose this is some compression 1 to 2, maybe some adiabatic compression on a PV. So जब हम कंप्रेशन करते हैं उस टाइम पे स्पेसिफिक वॉल्यूम डिक्रीज हो जाते हैं एंड डेफिनेटली प्रेशर बढ़ते हैं, है ना. सो जब V कम होता है एंड प्रेशर बढ़ता है, नॉर्मली द आइडियल केस ऑफ दिस कंप्रेशन इज आइसोथर्मल. लेकिन प्रैक्टिकली आइसोथर्मल कंप्रेशन करना बहुत मुश्किल है क्योंकि अगर आपको पता है कि cycle tube cylinder, if you fit a cycle tube cylinder and if you start pumping air, immediately cylinder gets hot, correct? So that's why practically increasing the temperature will create some complexity in compressing the air. Okay, so इसलिए हम क्या कहते हैं जनरली एक इंटरमीडिएट प्रेशर लेके सो सिस्टम को यहां तक स्टेज से कंप्रेशन करते हैं 2' तक एंड लेकिन यहां कुछ टेम्परेचर कंट्रोल करते हैं एंड फिर से कंप्रेशन करते हैं इसको लाइक दिस. सो दिस इज 3' maybe. So this stage where you actually cool the gas, during this portion what you do, you actually take the heat from the system, okay, from the gas actually. So this process what you are doing in between, let us suppose if this is A and this is B, this process A to B is called intercooling. Okay, so intercooling is always represented by this horizontal line on a PV diagram. Okay, and हमको बहुत सारे डेरिवेशंस भी है कि कितने प्रेशर पर इंटरकूलिंग करना है. ओके, मतलब दिस इज PL PH एंड आपको ये चाहिए कि PL से PH तक जाना चाहिए, लेकिन कुछ इंटरमीडिएट प्रेशर पर हम इंटरकूलिंग करते हैं. सो ऑप्टिमम वैल्यू क्या होता है, PI इज इक्वल टू ज्योमेट्रिक मीन ऑफ PH इनटू PL. ओके, सो दिस इज ज्योमेट्रिक मीन ऑफ PH एंड PL. ठीक है, so this we have a lengthy derivation for this. You know, but let us right now just keep this in mind because ये बहुत छोटा सेशन था PYQ से PYQ का सॉल्विंग. So इस लाइन बोलता है कि इंटरकूलिंग कर्व. So A to B is intercooling and इसके वजह से we will save this amount of load actually or work on the compressor. Okay, so this is saving in work of compressor. Actually, Okay, so saving of work in compressor, and this intercooling A to B is a horizontal line in this PV plot actually. Okay, so अगर आपने कुछ Breton cycle का compression intercooling techniques पढ़ा है तो ये question आपको बहुत आसान से solve करेंगे. So this AB is going to be intercooling, and normally जब मेरे जिंदगी में I have seen the compressor of 14 stages. Okay, जब मैंने HPCL में काम किया था उस टाइम पे एक compressor था, and there was 14 stages of compression, 10 low pressure stages and 4 high pressure stages actually. Okay, and 14 stage compression is what we have done, and both sides is we'll do intercooling also at for many gases we'll do the intercooling in between. Okay, and let us go to the next question quickly. Which of the following uses a regenerator? So tell me, in चारों cycle में, और I think 3 cycles have again, Breton, Ericsson and Stirling cycle. So in तीनों cycle में कितने cycle में and we'll use a regenerator. So पहले regenerator क्या होता है? So let us say this. This regenerator is nothing but a device which absorbs heat during some part of the cycle, and rejects heat during other part. Rejects, instead I would write something here, rejects same heat during second part, same amount of heat during other part of the cycle, actually, during other part of the cycle actually here. Okay, so this is called a regenerator. And जब हम एक cycle decide करते हैं, this Breton cycle में regenerator use करते हैं, लेकिन ideal Breton cycle लिया तो we don't use the regenerator. Ideal Breton cycle में क्या चीज मिलते हैं? एक compressor होते हैं and एक combustion chamber, normally एक turbine होता था, and we will eject the heat to the atmosphere. But in these two cycles, Ericsson and Stirling, हम क्या करते हैं? Heat addition and heat ejection हम एक regenerator के वजह से करते हैं actually. Okay, so that's why actually these are the two cycles which uses regenerator with ideal case. Okay, regeneration technique is used to increase the efficiency of this Breton cycle, but if you take the ideal Breton cycle, we do not use the regenerator actually. Okay, so that's why this Ericsson and Stirling cycle, in both these cycles, heat addition and heat rejection is operated by this regenerator. So that's why both B and C have this option. Okay, so this option is correct actually, both B and C in Ericsson cycle and also in Stirling cycle. In both these cycles, heat addition and heat rejection is managed by a regenerator. Okay, so it's actually D. D is the correct option in this particular case. So Ericsson cycle and Stirling cycle both will use a regenerator for the heat addition and heat rejection process. Okay, then let's go to the next question. So इस क्वेश्चन में थोड़ा सा कंट्रोवर्सी था, अब पता चलेगा कंट्रोवर्सी क्या है. A refrigerator with COP of 5 is used in a room of 300 Kelvin. Okay, so मान लो कि एक कमरे था 300 Kelvin इसका टेम्परेचर. Now we have a refrigerator cycle basically. Okay, so there is a refrigerator. For example, this is a refrigerator. Now what is the space inside the refrigerator actually? What is the temperature inside? Okay, that is not given, but COP is equal to 5. So coefficient of performance of this refrigerator is actually equal to 5. Correct? So अब हम solve करेंगे. देखिए, COP is equal to W or Q dot L, refrigeration effect. Basically, whatever the refrigeration effect that you want, divided by the work what you are supplying. W input that you are supplying generally. Okay. Now, this room temperature is 300 Kelvin. And inside refrigerator का temperature कितना है? ये हमको नहीं पता चला. But COP is given. Now let us read the question. What will be the heat intake through a section of the refrigerator wall of area 100 cm by 100 cm with a thickness of 10 cm, assuming only conduction. Okay, so you can see this is only conduction. Value of thermal conductivity of the wall can be taken as 1 watt per centimeter Kelvin actually here. Okay, so this is taken as 1 watt per centimeter Kelvin. So let us see. Thermal conductivity का value कितना है? 1 watt per centimeter Kelvin. So this we can write as 100 watt per meter Kelvin. Correct? अगर आपने convert किया तो this 1 centimeter is equal to 10 power minus 2 meters होगा, and this 10 power minus 2 is in the denominator, so 1 by 10 power minus 2 gives you 100 watt per meter Kelvin. So ये होता है कि thermal conductivity. Now मान लो कि एक रेफ्रिजरेटर का wall था, मतलब we have taken a small section here, then this area is given to you, correct? So this area, like for example, if you see, this is the refrigerator wall actually, and if you see the side view of this side view of this wall is 100 by 100. It's like a square box actually. Okay, so this is 100 by 100 actually. Okay, so 0.1 meter by 0.1 meter. Okay, so 0.1 meter, 100 centimeters, right? So 1 meter and 1 meter. Great. So this is 1 meter and this is also 1 meter. Now we know that heat getting transferred into the wall is actually equal to, so Q is equal to, this is a conduction, so the rate of heat transfer is what they are asking you, correct? So they are talking about the heat intake to a section, and heat intake is given in watts actually. So heat intake is equal to minus K area into delta T by delta X. And wall का thickness कितना दिया? 10 centimeters. Okay, so 10 centimeters means thickness is equal to delta X basically. The thickness value of this wall is actually equal to 10 centimeters, which is 10 power minus 1 meters. So आपके पास thermal conductivity का value है, area of the wall भी है, and delta X का value भी है, पर लेकिन delta T कितना है? Okay, so to calculate delta T, we know that wall के outside 300 Kelvin, लेकिन अंदर रेफ्रिजरेशन स्पेस का, रेफ्रिजरेटेड स्पेस का टेम्परेचर कितना है? सो इस चीज कैलकुलेट करने के लिए हमको सीओपी दिया था, लेकिन इसमें एक कॉम्प्लेक्सिटी था. अगर आपको सीओपी यूज करना है तो इन टर्म्स ऑफ टेम्परेचर्स क्वेश्चन में देना चाहिए कि ये रेफ्रिजरेटर रिवर्सिबल होना चाहिए. ऐसा नो रिवर्सिबल. सो अगर इस रेफ्रिजरेटर रिवर्सिबल नहीं है तो we cannot write COP in terms of temperatures, right? So we make an assumption because inside refrigerated space temperature is not given, so we assume that this refrigerator is actually a reversible refrigerator. So अगर इस refrigerator reversible है तो COP is equal to temperature of the refrigeration by TH minus temperature of the refrigeration again, correct? So under refrigeration का temperature पता नहीं है, and we know the outside temperature is 300. So this implies 5 times is equal to TL by 300 minus TL. So अगर आपने TL का वैल्यू कैलकुलेट किया तो कितना आएगा? 5 times of 300 minus 5 times of TL is equal to TL. So 6 times of TL actually, 6 times of TL is equal to 300. So TL is equal to 50 Kelvin, correct? So 50 Kelvin is the temperature. Now if you calculate this value, Q dot is equal to minus K. K का वैल्यू कितना है? 100 into area. You see, this is 1 meter and this is also 1 meter. So 1 into 1. ये होता है कि 1 meter square into delta T. Delta T का value कितना है? So outside it is 300, inside it is 50. That means if you take the wall of some thickness, for example, which is this delta X, then आपको पता है कि अगर यहाँ 300 Kelvin and during this wall it is 50 Kelvin, then temperature difference होता है कि 50 minus 300 minus 250 by delta X. So delta X का value कितना है? हमें calculate किया अभी 10 power minus 1. So 10 power minus 1. So this is the value actually here in this case. Okay. So if this is the value, then minus and minus gets cancelled actually here. Then 10 power minus 1 Q dot value is equal to 2500 and 0 watts. Actually 25 kilowatts तक value आएगा. Correct? Yes or no? ये 5000 is coming. Delta T is 250, right? This value, what is this value? 5 times of 300 is equal to, okay, this is 250, sorry. This is 250, correct. So if this is 250, then this value is 50. Temperature difference is 50. Then this value divided by 5, so 5000 watts actually. Yes, this is 5000 watts. So 5000 watts is actually the correct answer. Yes, TL 250 होना चाहिए, क्योंकि अगर इस इक्वेशन को आपने सॉल्व किया तो TL का वैल्यू 250 आएगा. ओके, सो अगर आपने TL इक्वल टू 250 केल्विन यहाँ सब्स्टिट्यूट किया तो टोटल वैल्यू 5000 watts आएगा. सो मतलब क्या होता है? Every second 5000 joules of energy is getting in because of the temperature difference actually here. Okay, so that's why 5000 watts is actually the correct answer in this case. लेकिन 5000 is the answer अगर if this refrigerator is reversible. Okay, लेकिन क्वेश्चन में उस उस ईयर पे 2020 में this question reversible word is not given, so इसलिए इस क्वेश्चन एड्स कर दिया था, सारे लोगों को मार्क्स दिया. ठीक है, फाइन. Are you all clear with this? A good question based on the concepts of refrigeration and also thermal conductivity, basically one-dimensional heat transfer case. Clear to all of you? TL will be more than 300 Kelvin. No, look, TL is the temperature inside the refrigerated space and 300 Kelvin is the temperature of the room actually here. Understood? So that's why room temperature will be higher than this refrigerated space temperature. Clear? अगर आपकी कैलकुलेशन में 300 से ज्यादा वैल्यू आए तो डेफिनेटली आपको कैलकुलेशन में कुछ गलती है. Okay, you have to do the calculation again. Clear? You know, think about this concept basically. अगर if you calculate this, if this is 300 Kelvin, refrigerator cool होते हैं ना. Actually, when you compare with room, refrigerator space will be, you know, at low temperature, which is very common intuition, and इसलिए इसका value 250 Kelvin, 300 से नीचे होना चाहिए. ठीक है? So let us solve this question. A mass of 1 kg of air at 27 degrees Celsius and 0.98 atmosphere is taken through a diesel cycle. So पहले हम diesel cycle का PV diagram बनाते हैं. So let us plot this. PV actually here. Then diesel cycle में compression is isentropic 1 to 2. I'm just giving you some idea. So this is isentropic compression. Now diesel cycle में heat addition होता है कि constant pressure heat addition. Yes or no? So now if you see, actually ये constant pressure क्यों बोलते हैं? ये सारी चीजों का बहुत explanations था actually, but you know right now हम straight away इस questions का solve करने का session में है, so इसलिए फटाफट हम questions solve करेंगे. Okay? So लेकिन अगर आप कुछ detail जब YouTube का course करते हैं उस time पे अगर time हुआ तो मैं आपको clearly explain करता हूँ कि इस diesel cycle में heat addition constant pressure क्यों होता है? In case of Otto cycle heat addition constant volume heat addition क्यों होता है? So ये चार चीज मैं आपको explain करता हूँ. लेकिन अभी देखिए, so constant pressure heat addition, then P is equal to constant, okay, and you know this expansion is again isentropic and constant volume heat rejection. Okay, so constant volume heat rejection. आप किसी भी IC इंजन का साइकिल देख लो, this process will be always at constant volume. There's a very important reason for that. Okay, we will learn that again. So see, this is of course at constant volume. So they have given the state 1 conditions. So mass of 1 kg of air. So mass कितना था? 1 kg and of air at 27 degrees Celsius. So T1 का वैल्यू कितना है? 27 degrees Celsius. अगर आपने केल्विन में कन्वर्ट किया तो 300 केल्विन, करेक्ट? And 0.98 atmosphere. So P1 is 0.98 atmospheric pressure. आप सबको पता है कि 1 atm is equal to 101.325 pascal. So अगर आपने इस atm को किलो पास्कल में कन्वर्ट होना चाहिए तो multiply with 101.325 किलो पास्कल्स. Okay, so 0.98 into 101.325 किलो पास्कल्स. इसका वैल्यू होता है कि you know around some 9900 किलो पास्कल्स around. Okay, so now continue the question. If the compression ratio of the engine is 16, so what is the value of compression ratio? If this value is V1 and if this value is V2, then ये लोग ने दिया कि V1 by V2 is equal to 16, correct? So this is the compression ratio. Calculate the temperature of the air after the compression. मतलब जब compression खत्म करते हैं, so second state पे आएगा, so T2 का value कितना है? Okay, so what is the temperature of this cycle at this state 2? This is what they are asking. So this 1 to 2 is adiabatic process, yes or no? So and this substance is taken as air. So air को हम ideal gas assume किया तो then T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1, correct? So T2 is equal to T1 times of V1 by V2 whole power gamma minus 1. So T1 का वैल्यू कितना है? 300 केल्विन and V1 by V2 इनका वैल्यू कितना है? V1 by V2. So V1 by V2 is 16. So 16 power गामा कितना दिया? 1.4 नॉर्मली, लेकिन कुछ कैलकुलेशंस की इजीनेस के लिए 1.5 दिया था यहाँ, करेक्ट? सो 1.5 minus 1 which is 0.5. 0.5 मतलब स्क्वायर रूट, करेक्ट? सो 300 times of 16 power 0.5 actually here, okay? And this value is 4 actually, so 4 into 300 is equal to 1200 Kelvin. So this is the temperature after compression. So 1200 Kelvin. And देखिए, this question is very important. This value is 1200, but this units is degree Celsius. लेकिन हमारा value कितना है? 1200 Kelvin. Okay, so this you have to be little careful in eliminating this option. बहुत सारे लोग ये कहते हैं कि 1200 देखने के बाद उसको टिक करते हैं. Okay, but लेकिन 1200 is given in degree Celsius, so that's the wrong answer. So 1200 minus 273. This gives you 927 degrees So 927 degrees Celsius is the correct answer in this case. Okay. सॉल्व करने के बाद बहुत लोगों को लगता है कि ऑप्शन ए इज द करेक्ट आंसर, लेकिन वो डिग्रीज में चेक करना है. ओके, सो यूनिट्स इज गिवन इन डिग्री सेल्सियस, लेकिन हमको वैल्यू आएगी इन केल्विन. ओके, सो दिस इज 1200 केल्विन. क्लियर टू ऑल ऑफ यू? ओके, सी इज द करेक्ट आंसर. हाउ मेनी ऑफ यू हैव थॉट दैट ए इज द आंसर? टेल मी हॉनेस्टली. हाउ मेनी ऑफ यू एक कैलकुलेशन करने के बाद इसको देख के यू फेल्ट दैट दिस इज द आंसर? Definitely there will be some people. Tell me honestly. क्योंकि लास्ट टाइम ये मिस्टेक किया बहुत सारे लोग ने इस क्वेश्चन की. Okay? Yeah, you have to be little careful. Fine. So let us solve this question. An aircraft is in its takeoff roll at sea level. इस क्वेश्चन में भी ऐड कर दिया था लास्ट टाइम. I'll tell you why. See here. An aircraft is in its takeoff roll at sea level with ambient temperature of 18 degrees Celsius. So T infinity कितना दिया था? T infinity is equal to 18 degrees Celsius. Fine. What is the approximate speed of the aircraft if the temperature measured by a probe at the exit of the engine diffuser? Okay, so diffuser will be at the last part, correct? So basically, if you see aircraft engine, you all know that an aircraft engine will be modeled something like this. So in the beginning, you got some diffuser actually here. So this part, during this part, a probe attached at the beginning of this aircraft diffuser. Okay. So let us suppose there is a probe at this engine. Now, whenever you check the units, good. Okay. So now whenever this is the engine, basically, and this is the probe. Okay. So probe and this stagnation temperature. कितना मेजर किया? 36 degrees Celsius. Okay. So this is 36 degrees Celsius. Now, this concept is called stagnation concept. To explain this concept, because this concept बहुत important है ISRO exam के लिए, and every time there comes a paper of ISRO, you will find some question related to this. So that's why I have kept you some understanding from my class notes where I have taught this concept of stagnation properties actually to some understanding. Look, मैं आपको दिखाता हूँ stagnation properties. Okay, I hope you can see the notes. Screen clear है सारे लोगों को? You can see the screen clearly? Okay, so now stagnation point is that point where the local velocity of the flow is basically 0. Okay, so actually क्या होता है, अगर आपका diffuser है तो ऐसे, now when airplane is moving, then the air will also try to flow like this, and this plane will also come. So at this point exactly, the velocity of the points will be locally 0. So A points को हम बोलते हैं कि stagnation points. Okay, so practically stagnation point का definition ये होता है कि अगर एक ideal gas is flowing, then when it hit a body, the complete particle is brought into rest isentropically. Then that point where the local velocity is 0 is called stagnation point. And after some analysis, you will find out the relation by using the steady flow energy equation and all. Actually fluid mechanics class से notes का copy था. So now if you take this and if you simplify this, you will end up with this expression: stagnation temperature is equal to T1. T1 का मतलब इस stagnation point से बहुत दूर में fluid flow होते हैं, and इस point का temperature actually. Okay, so T1 plus V square, velocity at which the particle is coming. Normally in quiescent air, let us suppose A is stationary, and if the vehicle is moving, then you can approximate the same case as vehicle is stationary and A is moving in the opposite direction. Okay, so both are same. So V square is the velocity square of the vehicle and divided by 2 times of Cp. लेकिन एक चीज बहुत ध्यान रखना, this is in Kelvin and this is in meter square per second square. So this Cp should be substituted in actually joule per kg Kelvin. Okay, it should not be in kilojoule per kg Kelvin. This has to be substituted in joule per kg Kelvin actually here. Okay, now if you solve this question, so this is 36 degrees Celsius minus 18. So this difference should be equal to V square by 2 times of Cp. Okay, so ये formula बहुत ध्यान से याद रखना. Ts is equal to T infinity plus V square by 2 Cp. लेकिन जब आप ये फॉर्मूला अप्लाई करते हैं उस टाइम पे एक चीज ध्यान रखना है कि Cp का वैल्यू जूल पर केजी केल्विन में लिखना है. ओके, सो दिस Cp V square by 2 Cp. So this Cp वैल्यू, इस Cp का वैल्यू हमें जूल पर केजी केल्विन इसमें रखना है. ओके, नहीं तो our answer will become wrong. Okay, because everything is in normal SI units, you cannot put this in kilojoules per kg Kelvin. Clear? So now if you see this temperature difference, Ts minus T infinity, so temperature difference degree Celsius या Kelvin, दोनों units में same होते हैं. So 36 minus 18 is equal to V square by 2 Cp. So 18 into 2 into Cp. So Cp का वैल्यू कितना दिया था? 1 kilojoule per kg Kelvin. So 1 kilojoule मतलब 10 cube actually. Okay, so 10 cube joule per kg Kelvin is equal to V square. So V is equal to 36 into square root of 36 into 1000 actually. Okay, so 36 into 10 cube meters per second. So square root of 36 is 6 and this is 600 into root 10 actually. Okay, so 600 times of root 10. 600 times of root 10 meters per second, around 1800 meters per second at that velocity. But you can understand in these options which were given in this case, they did not convert this in kilojoule per, they did not convert this in joule per kg Kelvin actually. Okay, because you can clearly see square root of 36 is 6 into square root of 10 cube actually. Okay, so square root of 10 cube is actually square root of 100 into 10. So 6 into 10 is 60. Okay, 60 into square root of 10 actually here. 60 into square root of 10 meters per second, around 189 to 200 meters per second. Like if you see these values, these are 12, 3, 6, 18, and actually that here answer was given as 6, but actually 6 is wrong answer. Okay, because if you want to get 6, you have to keep this 1 here. Yes or no? Then V square is equal to 36, V is equal to 6 meters per second आएगा. लेकिन this keeping 1 here is wrong because this Cp has to be substituted in joule per kg Kelvin. Clear to all of you? Did you all understand what is the mistake in this question? Actually, that was given by ISRO at that time. This has to be substituted in joule per kg Kelvin. लेकिन answer दिया था कि kilojoule per kg Kelvin basis में. Okay, so that's why this year, that year, that question was deleted by for marking actually. Clear to all of you? Mehul, Rishikesh, Panit, Manikanta, every one of you. So is this clear to all of you? So please type in the chat box. Got it? So actually 6 is not the answer because 6 will be the answer if you substitute this Cp in kilojoule per kg Kelvin. लेकिन this value को हम joule per kg Kelvin में substitute करना है. ठीक है? So please keep this formula in mind. I think even this year there comes one question based on this. Okay? So इसलिए एक चीज बहुत important है. So इसलिए मैंने थोड़ा PDF का notes भी दिया आपको. So you can see this is the stagnation properties where we discuss a bit about, and normally this is temperature, so इसको भी temperature का dimension होना चाहिए, correct? So this term is called dynamic temperature. अगर किसी ने पूछा तो कुछ एग्जाम में इस condition का dynamic temperature क्या होता है? So V square by 2Cp इस value is actually equal to the dynamic temperature. हम इसको dynamic temperature क्यों बोलते हैं? क्योंकि this is due to the velocity and also अगर आपने इस equation में देखा तो सारी चीजों का dimension same होना चाहिए. So इन दोनों चीजों का dimension temperature. So this dimension should also be temperature as per dimensional analysis. Clear? So that's why we'll see this as dimension temperature, and you can clearly see this is the values of gamma and all for different gases that I have told at that time. So stagnation pressure. Okay. So stagnation temperature पता है तो stagnation pressure भी calculate करना है क्योंकि P1 into T1 by Ts. Okay. My speed of talking is very high. Okay, got it. थोड़ा कम करना है, ठीक है? So P1 into T1 by Ts whole power gamma by 1 upon gamma. So actually ये derivation हम इसके adiabatic flow के अनुसार करते हैं. And finally you can also see stagnation pressure, stagnation density, इन सारी चीजों का मैंने फॉर्मूला दिया था उस टाइम पे, लेकिन आपके सेशन के लिए ये स्लाइड्स बहुत इंपॉर्टेंट है इस ये सारा एग्जाम के लिए. सो दैट्स व्हाई आई हैव केप्ट दिस नोट्स इन दिस पीडीएफ. सो अगर आपको पीडीएफ मिलेगा तो ये सारे स्लाइड्स भी आपके साथ होंगे, ठीक है? सो प्लीज गो थ्रू दिस लिटिल केयरफुली, यू विल गेट द आंसर्स. लेकिन एक कॉन्सेप्ट ऑफ स्टैग्नेशन इज वेरी इंपॉर्टेंट इन फ्लूइड मैकेनिक्स. सो जब मैंने फ्लूइड मैकेनिक्स पढ़ा था उस टाइम पे कंप्रेसिबल फ्लो भी है, सो उस टाइम पे मैंने पढ़ा है, ठीक है? नाउ लेट्स गो टू द नेक्स्ट क्वेश्चन. Next, go to the next question. The combustion ratio for diesel engines is close to. Now, you know that generally it is around 16 or 18 within that range. So, you can see for auto engines or SI engines, generally you can say SI engines or petrol engines, you can see this will be within the range of 8 to 12 generally here. Below 8 it is difficult because आप सब लोगों को ये equation पता है? Thermal efficiency of auto is equal to 1 minus 1 by r power gamma minus 1. देखे इस इक्वेशन को कभी भी? Have you ever seen this equation? Have you ever seen this equation? Yes? Normally thermal efficiency of Otto cycle. अगर आपने कुछ thermodynamic analysis किया तो Otto cycle को, तो इस इक्वेशन मिलेगा आपको एफिशिएंसी के लिए. ओके, एंड ऑल्सो ये वैल्यू होता है कि 1 माइनस T1 by T2. बस अगर आपको T1 and T2 टेम्परेचर्स पता है तो यू कैन कैलकुलेट द एफिशिएंसी ऑफ दिस साइकिल एक्चुअली. ओके, बिकॉज यू कैन सी T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. So this V1 by V2 whole power gamma minus 1 is equal to T2 by T1, and इसको हम बोलते हैं कि कंप्रेशन रेशियो. सो R power gamma minus 1 is equal to T2 by T1 जनरली. सो अगर आपको ऑटो साइकिल में at the beginning of the compression and at the ending of the compression इन दोनों values का temperatures इन दोनों locations का temperatures पता है तो you can simply calculate the Otto cycle efficiency by this simple calculation. Okay, no need to calculate R then power gamma all these calculations, and बहुत सारे questions में ये दोनों data देते हैं लेकिन हमको ये point पता नहीं है. So इसलिए हम क्या करते हैं, R calculate करते हैं and इस calculation calculator use करके बनाते हैं. Okay, so that we need not do that because 1 minus T1 by T2 is actually here. Okay, so normally इस question में एक बहुत अच्छे interview question भी था. I'll discuss it now. So see here. Normally, अगर R बढ़ा तो, let us suppose if R is increasing, compression ratio is increasing, तो efficiency को क्या होता है, बढ़ेगा या नीचे आएगा? Type in the chat box. अगर आपने compression ratio को बढ़ा किया तो, so what happens to thermal efficiency? ये बढ़ेगा? नहीं तो it will decrease. Type in the chat box. It will increase, correct? It increases. Everyone type in the chat box. This value will increase. लेकिन practically इसको एक limit था. क्यों? Because our value generally 8 to 12. Okay, so we generally don't go beyond 12 and all sometimes. क्योंकि जब engine का compression ratio 12 से ज़्यादा हुआ तो the pressure which is building in the air will be large such that when this air fuel mixture is getting compressed, some auto ignition happens in between, okay, which creates knocking. That's why this, to avoid this knocking, we will restrict a compression ratio. And but in diesel engines, diesel को थोड़ा higher auto ignition temperature था, so इसलिए normally 16 to 22. This is the range that we practically do in general cases. So that's why is in चार options में this 15 to 20 is the option which is very close to this diesel engines. So that's why this is taken as the range. Normally diesel engines में 16, 18 or within the range actually. Okay, so within that range we operate the diesel cycles. Clear? Now let us solve this question. 1 kg of carbon monoxide requires how much quantity of oxygen to produce 11 by 7 kg of carbon dioxide gas? Good. पहले ये बोलिए, what is the equation of carbon plus oxygen gives carbon dioxide? Okay, they ignite by combustion. Yes, in the previous case. Okay, so 1 kg of carbon monoxide, ठीक है, कुछ carbon monoxide है हमारे पास, and also O2 gives CO2. So now we want 1 kg of carbon monoxide. So carbon monoxide का weight कितना दिया? 1 kg. Requires how much quantity of oxygen? कितना गैस ऑक्सीजन चाहिए कि CO2 कितना प्रोड्यूस करना है? 11 by 7 kgs. Now, बहुत सारे लोग एग्जाम में ये मिस्टेक करते हैं कि इन इक्वेशंस को बैलेंस करने का कोशिश करते हैं, लेकिन बैलेंस करने का जरूरत भी नहीं है. क्यों? लुक, क्योंकि मेरे को भी एक्चुअली एग्जैक्टली ये इक्वेशन होता है as far as I know in combustion half O2 gives CO2. Okay, so 2CO plus O2 gives rise to 2CO2 actually. Okay, लेकिन मेरे को भी मान लो कि इस इक्वेशन नहीं पता चला मेरे को. Then everywhere you see there should be mass balance. Yes or no? Mass balance is the common thing that should happen. अगर आपके पास कुछ reactants है तो एक chemical reaction हुआ and आपको कुछ products भी मिला. Now tell me one thing. Reactants का mass mR, products का mass mP. ये दोनों equal होना चाहिए या नहीं? Mass should be conserved, correct? Reactants में कितना mass है उतना products भी आना चाहिए, नहीं तो we are not obeying mass conservation, correct? So that's why you can see total mass of the reactants is always equal to total mass of the products. No need to balance the chemical reaction, nothing. Okay, just write this. So now if you see 1 kg of carbon dioxide is there, products is coming 11 by 7 kgs. So oxygen का weight कितना होना चाहिए? Mass of oxygen is equal to 11 by 7 minus 1 which is 4 by 7 kgs. Option A बस. ओके सिर्फ सिंपल मास कंजर्वेशन से इसका वैल्यू कैलकुलेट करना है. ओके बहुत सारे लोग यहाँ इक्वेशन बैलेंस करने की कोशिश करते हैं एंड कुछ लोग फील करते हैं कि मेरे को इक्वेशन पता नहीं चला सो हम कैलकुलेशन कैसे करेंगे. सो यू डोंट नीड ऑफ एनी दोस थिंग्स, यू जस्ट नीड टू नो मास बैलेंस इक्वेशन. अगर आपको मास बैलेंस इक्वेशन पता है तो यू कैन डेफिनेटली सॉल्व दिस क्वेश्चन. ओके बिकॉज मास ऑफ द रिएक्टेंट्स शुड बी इक्वल टू मास ऑफ द प्रोडक्ट्स, क्योंकि प्रोडक्ट्स बनाते हैं लेकिन नया मास we cannot bring inside. Okay, so that's why whatever is the mass of the reactants, that same should be the mass of the products actually. So अगर आपके पास कार्बन डाइऑक्साइड और ऑक्सीजन है तो CO2 प्रोड्यूस हो जाएगा and CO mass is given as 1 kg and CO2 is given 11/7 kg. So अगर आपको ऑक्सीजन का मास चाहिए तो इन दोनों मास से CO2 मास से this CO का मास सेपरेट करना है बस. If you can separate then you will get the value. So this is 4/7 kgs. This value is 4/7 kgs actually here. Okay. Now, let us go for the next question. For a two-stage reciprocating compressor, combustion from P1 to P3 is with perfect intercooling and no pressure loss. If combustion in both the cylinders follows the same polytropic process and the atmospheric pressure is PA, then the intermediate pressure P2 is given by. So, as I was telling you, for perfect intercooling, कुछ mathematical derivation करना है, actually differentiations है कुछ. For perfect intercooling, this intermediate pressure should be equal to geometric mean of the low pressure and high pressures. Okay, so this is like geometric mean. Pi is geometric mean. Geometric mean actually here. So we are doing the compression in two stages. PL से PA तक एक compression करते हैं and PI से PH तक दूसरा compression करते हैं. Okay, लेकिन PI का value कितना मिलेगा? PH of PH into PL with a square root actually here. Okay, and many times if you go for three-stage compression, okay, so you have to set this PL, P1, P2, PH in geometric progression. मतलब if this is A, if this is AR, then AR square, AR cube. This will be the optimum. You can do the derivation actually. मेरे पास था लेकिन I felt that it will be very mathematical right now, so that's why I have given you this actually. Okay, so whenever you have intercooling, this intermediate pressures ऐसे set होना चाहिए कि they should be in the geometric means of the initial and the final values actually. Okay, so that's why this option B is actually the correct answer. P2 is equal to square root of P1 multiplied with P3 actually here. Okay, अगर आपके पास 3 stage intercooling है तो then definitely you can see all these stages will be set in intercooling in the geometric ratio actually here. So this will be in geometric progression. Geometric progression. जब आप बेटॉन साइकिल पढ़ते हैं उस टाइम पे आपको पता चलेगा कि अगर आपका इंटरकूलिंग परफेक्ट होना चाहिए तो द इंटरमीडिएट प्रेशर्स व्हिच यू आर सेटिंग शुड बी इक्वल टू, इट शुड बी इन दिस ज्योमेट्रिक प्रोग्रेशन. ओके, नॉर्मल इस टाइम पे कैसे लेते हैं, वर्क डन इन पॉलीट्रोपिक प्रोसेस का एक्सप्रेशन लेते हैं हमें. सो वर्क डन इन लो प्रेशर कंप्रेसर प्लस हाई प्रेशर स्टेज एक्चुअली. सो इन दोनों का एक फॉर्मूला लिख के डिफरेंशिएट करते हैं विद रिस्पेक्ट टू पीआई. ओके, सो आफ्टर ए बिट ऑफ एनालिसिस मैक्स मिनिमम कांसेप्ट यूज करने के बाद आप लोगों को एक एक्सप्रेशन आएगा. इंटरमीडिएट प्रेशर इज इक्वल टू स्क्वायर रूट ऑफ लोअर प्रेशर multiplied with higher pressure. Okay, so for now please keep this point in mind. So this P2 is equal to square root of P1 into P3. Clear to all of you? So are you all clear till this point? So please type in the chat box. Is everything clear till this point? आइए एक बार chat box में बोलिए. So please type in the chat box. आपके लिए मैंने हिंदी भी सिखाया ये 6 महीने में. Okay. जब मैंने पीडब्ल्यू में ज्वाइन हुआ जब सितंबर अक्टूबर उस टाइम पे मेरा हिंदी बहुत बर्बाद है उस टाइम पे. ओके, लेकिन मैंने थोड़ा हिंदी सीखा एंड वी हैव ट्राइड लॉट ऑफ थिंग्स सो दैट नाउ इट्स समथिंग बेटर. ओके, इवन आई नो दैट देयर आर मेनी मिस्टेक्स इन माय हिंदी नाउ, especially with the prepositions ka, ke, ki, these things, but still I'm managing for you. Okay, I hope you are understanding the things, right? At least my Hindi is at understandable level, not to the excellent level of degrees, but it is at understandable level. Clear? Correct? Yes or no? Type in the chat box here. Pranit Rishikesh HKR. Right? बहुत सारे names, नए names हैं. Actually आज ESC mains का exam भी हुआ था and actually thermal fluids mechanics मैंने questions भी देखा and they were like some of the like every year very classical questions came this year, so it can be like easily solved with the help of notes and all these things. But anyway, so ISRO is one very good option. Like ISRO ऐसा option होता है कि when you go to ISRO, because I have personally seen VSSC, Vikram Sarabhai Space Center. Normally जब मैंने IIT मद्रास में PhD में enroll किया था, उस टाइम पे actually IIT मद्रास में एक lab था, like एक lab है अभी भी, okay? So NCCRD, National Combustion Center for, you know, National Combustion Center, NCCRD. I forgot the name full form. Actually, we call this NCCRD, National Center for Combustion Research and Development. Yeah, ये नाम था. Okay, so National Center for Combustion Research and Development, Research and Development basically R&D. So basically, if you see IIT Madras, IISc Bangalore, ISRO, ये तीन मिलके यहाँ center IIT Madras में you know डाल रहा. I'll show you the picture actually of NCCRD. You will have a glass engine also in NCCRD. क्योंकि जब मैंने IIT मद्रास में था उस टाइम पे मैं भी देखने का मौका मिला. सो ग्लास इंजन होते हैं एंड नॉर्मली ग्लास इंजन में हम कंप्रेशन ये सारे प्रोसेस कैसे देखते हैं, बिकॉज ग्लास अगर आपके पास ग्लास इंजन तो भी every cycle happens in some milliseconds time. Okay, let us suppose if engine is running at 1500 rpm, 1800 rpm, उस लेवल पे अगर इंजन का स्पीड है तो so every cycle बहुत कम टाइम पे होते हैं, है ना. so उस टाइम पे हम क्या करते हैं, अगर मान लो कि ये सिलेंडर था, इसके सामने एक कैमरा भी डालते हैं. कैमरा से वीडियो रिकॉर्ड करते हैं. उस वीडियो को बहुत लो स्पीड से प्ले करते हैं, so we can see the combustion and all happening in that engine actually. Okay, there's a glass engine facility there. If you find time, so you can go there. Okay, so this also has a tie-up with Vikram Sarabhai Space Center, Thiruvananthapuram basically. So एक बार मेरे को मौका मिला था, एक बार मेरे को भी मौका मिला था कि VSSC में जाने के लिए, एंड IIST, Indian Institute of Space Science and Technology, ये भी था त्रिवेंद्रम पे. So I'll show you these pics actually. NCCRD, IITM. So you can see National Center for Combustion Research and Development. Okay, so ये था हमारा main website and that's the building. At that time the fourth floor was under construction at that time when I was there. But you can see once you go into the lab you can see a lot of new things here. NCCRD, National Center for Combustion Research and Development. It's a joint venture by ISRO, ISC Bangalore, and also IIT Madras. Okay, so you can see normally we have some 19 MS students and 49 PhD scholars around working there. So we can see automotive combustion. These are different wings in the NCCRD. This is the entrance actually here. So we can see a lot of things, and also VSSC, Vikram Sarabhai Space Center. So if you see this, that's VSSC basically for you. And if you look at some images, there'll be, it's a good campus again. Okay, so you can see all the, this is the launch pad actually at VSSC, and we can see this is the entrance basically, the main entrance, all these things. So अगर जब आपने एग्जाम का तैयारी करते हैं उस टाइम पे इस टाइप का फोटोज देखा तो बहुत मोटिवेशन मिलेगा आपको. ओके, जब मैंने बाग क्लियर किया उस टाइम पे मैंने NFC न्यूक्लियर फ्यूल कॉम्प्लेक्स का पिक्चर्स बहुत सारे बार देखा था, एंड मैंने इंटरव्यू बहुत आसानी से क्लियर किया उस टाइम पे. Okay, so that's why we have to look at these kind of pictures so that we'll get little motivated to study actually. Okay, study ऐसा नहीं करना है कि एक बुक डाल के बहुत पढ़ना है, नहीं, एक स्ट्रेटजी होना चाहिए. अब अगर पढ़ने की वजह से कुछ लो हुआ तो फिर how to gain back the energy, how to get motivated, ये चीज बहुत important था. Okay, so the first launch pad of India, yes, the first launch pad of India is in VSSC, Vikram Sarabhai Space Center, Bangalore. So I luckily had a chance to visit there when I was in my IIT Madras that time. So anyway, so let us continue this question. So पहले हम एग्जाम क्रैक करेंगे, उसके बाद इंटरव्यू के लिए कुछ चीज सिखा के then we'll go for the interviews. ठीक है? So let us start here. The heat envelope from the refrigerated space is 7.2 kilowatts and the power input to the compressor is 1.8 COP4. Anyway, let me draw this cycle. So एक refrigeration cycle है हमारे पास. So this refrigeration cycle is taking in some heat. So refrigeration effect कितना है इस cycle का? So this is taking a heat of refrigeration effect. Is refrigerated space is 7.2 kilowatts. So this is 7.2 kilowatts and it is rejecting to some high temperature and it is also taking some work. Work का value कितना है? 1.8 kilowatts दिया था. So 1.8 kilowatts. So अगर इन दोनों चीजों को हमने मिले तो 9.0 kilowatts. So this is the heat ejected to the outer space. Okay. So therefore this value is the refrigerated effect, refrigeration effect basically here. So this is the refrigeration effect and this is the work input to the compressor, W dot in. So आपको COP का वैल्यू होना चाहिए. So COP क्या होता है? Refrigerated space or the refrigeration effect, whatever the heat coming from the refrigeration space divided by work input to the compressor. So 7.2 is the heat ejected from this or heat taken from this refrigeration space and W dot work to the compressor is 1.8. So this value is 4. So COP का value 4. Yes. Okay, so value of the COP is actually 4 in this case. So the coefficient of performance of this refrigerator is basically 4 in this case. Clear? Very simple question. Look, guys, every device के लिए the formula of efficiency या COP is common. Okay, so बहुत सारे लोगों को ये confusion होता है कि किस चीज को numerator में लिखना है, किस चीज को denominator में लिखना है. Okay, so efficiency or coefficient of performance, anything, if you see what you are expecting from the machine, that's called desired effect. रेफ्रिजरेटर से हम क्या एक्सपेक्ट करते हैं? रेफ्रिजरेटेड स्पेस से कुछ हीट बाहर आने का एक्सपेक्ट करते हैं. एंड टू गेट दिस इफेक्ट, व्हाट इज द इनपुट यू आर गिविंग? सो दिस इज द कॉमन फॉर्मूला फॉर एफिशिएंसी और सीओपी, व्हाटएवर यू टेक. ओके, नॉर्मली जब आप एक हीट इंजन लिए तो हीट इंजन में क्या होते हैं? हीट इंजन नॉर्मली कुछ वर्क डिलीवर करते हैं. सो द डिजायर्ड इफेक्ट, व्हाई यू आर रनिंग ए हीट इंजन? टू गेट सम वर्क आउट ऑफ दैट. सो W डिवाइडेड बाय उस W हीट इंजन से लाने के लिए हीट इंजन को क्या देते हैं? QS एनर्जी. सम QS amount of heat is supplied to the heat engine, so W by QS. Okay, so this is how you get the definition. So these definitions are same for each and every device. Okay, so efficiency, COP, the names could be different, but the performance measure is same for all the devices. Okay, so desired effect. Like for example, अगर आपने COP of refrigerator calculate किया तो refrigerator से हम क्या expect करते हैं? Cold space से heat बाहर लेना expect करते हैं. So 7.2 basically QL, heat ejected from the lower temperature reservoir, divided by is heat लाने के लिए W dot is given to the compressor, so W dot. So every formula is same. In case of heat pump, we expect QH to be entering into the hot space, so QH divided by W dot. So yes, which is इस calculation से आते हैं. Okay, so anyhow here the COP is simple calculation, 7.2 divided by 1.84. Then a centrifugal compressor is suitable for which of the following? Fantastic, good question. Look, normally if you take the centrifugal compressors, this will be operating under two conditions. When the pressure difference you have to create is low pressure ratio. What are the words they have used here? Pressure ratio and mass flow. So low pressure ratio and high mass flow generally. High mass flow. Normally ये होता है कि I'll tell you some small story of HPCL. Okay, what happened? Normally let us suppose ये विशाखापट्टनम and मान लो कि ये सिकंदराबाद. There is a pipeline directly underground from Visakhapatnam to Secunderabad actually. Okay, normally it is called VSSPL, Visakhapatnam Secunderabad underground pipeline actually. So in pipeline क्या होता है? Let us suppose if petrol or diesel is flowing in, water spirit or diesel, then because of the friction loss, the pressure of the fluid will drop actually. हम सबको पता है कि HL is equal to FLV square by 2GD, V average square by 2GD, ये पता है हमको. So for every some distance, what happens? The pressure of the fluid will drop actually. Okay, the pressure will fall because of the friction. Now, if you want to send the fluid till here effectively, you have to maintain that pressure, correct? So इसलिए बीच में every 20-30 किलोमीटर के बीच में एक बूस्टर पंप हाउस होते हैं. ओके, सो बूस्टर पंप हाउस में क्या होते हैं? बूस्टर पंप्स होते हैं and these pumps will be centrifugal pumps generally. I think I have written compressors, it is pumps. Okay, compressors or pumps generally. In both cases the principle is same, so centrifugal compressors or pumps. So in this case of pumps, what happens? The pressure ratio, because क्योंकि head loss value due to the friction will be less because within that small space, but actually इस पाइप में बहुत सारे ऑयल फ्लो होते हैं. ओके, सो मास फ्लो रेट विल बी वेरी हाई इन जनरल, इवन इन टर्म्स ऑफ कंप्रेसर्स और बेसिकली इन पंप्स. इवन इन कंप्रेसर्स व्हेन यू आर डीलिंग विद गैसेस, द मास फ्लो रेट ऑफ द गैस विल बी हाई, but the pressure ratio, because we need not build the pressure completely like in the case of boiler or something, whatever pressure is lost, so the same amount of pressure should be increased actually in this case. So that's why low pressure ratio, and this is high mass flow actually here. Okay, so low pressure ratio and high mass flow is suitable for the centrifugal operations. Okay, basically this mass flow rate is very high in terms of centrifugal compressors generally. Okay, that's why these are the, normally this equipment comes under rotary compressors and rotary equipment actually. Normally in maintenance division I used to work under rotary, so I used to see all these devices, compressors, pumps and turbines. Okay, we have seen gas turbines pretty much, and we have gone for the shutdown and maintenance of gas turbines. So these things are very important actually, right? So let us solve this question. In a gas turbine power plant, reheating of the gas between high pressure and low pressure turbine stages will improve turbine output, decrease turbine output, increase compressor work, decrease compressor work. So मान लो कि हमारे पास एक TS डायग्राम है. बैटॉन साइकिल का, so TS. Okay, so pressure limits, these are the final pressure limits, but also there is an intermediate pressure limit. Okay, now if you are reheating the substance, reheating का हम कैसे करते हैं? पहले isentropic compression करते हैं 1 to 2 and उसके बाद constant pressure heat addition करेंगे, correct? So constant pressure heat addition and उसके बाद हम expand करेंगे to some intermediate pressure. So यहाँ से फिर हम इस temperature को reheating करेंगे, yes or no? So this reheating, normally in case of ideal reheating, we will reach again the same temperature and then we will expand to this low pressure, which is the heat ejection. Normally atmosphere will eject in case of gas turbines and all. And finally, we will have this heat ejection process. Okay, so this is heat addition, this is also heat addition. And this is the work done in high pressure turbine. So let us suppose if this is 3 to 4 and this is 5 to 6 for example. So this turbine is operating, means basically how we decide high pressure turbines and low pressure turbines. Okay, so based on the inlet to the turbine actually. Okay, so point at 3 is at high pressure as compared to point at 5. ऐसा हो क्योंकि अगर आपने नीचे से ऊपर गया तो this is pH, PL and this is PI. Okay, so this is pH, PI and PL. Now if you see this turbine has the inlet at low pressure comparatively. So that's why this expansion or this turbine is basically called the low pressure turbine, LPT बोलते हैं, and इसको बोलता है कि HPT, high pressure turbine. Okay, so now if you see this case, reheating की वजह से compressor में कुछ effect है या नहीं? Is there any effect on this compressor because of this reheating? Actually, reheating की वजह से compressor की load में कुछ change है क्या? No, correct? So there is no change in the efficiency or basically operating conditions of the compressor actually. लेकिन so no effect on compressor. No effect on compressor. लेकिन work output of the turbine क्या हो जाएगा? It will be increased, correct? So work done by the turbine will increase. This will increase actually. Turbine का work output increase हो जाएगा. क्यों? Because you can see high pressure turbine में कुछ work मिलेगा आपको and also in the low pressure turbine. Okay, so that's why this total work output of the turbine will increase. Okay, total work output from the plant will increase, लेकिन compressor में कुछ effect नहीं होगा. ठीक है? So that's why we will say that this value is actually increasing, you are improving turbine output actually here. Okay, so total work output from the turbine will increase because you can see this, there is one heat addition, one expansion and also there is second expansion totally. But of course, compared to this work expansion, generally sometimes this work expansion will be less, but that also depends upon the pressure ratio again. Okay, because this expansion stages will be large as compared to this expansion stages. Clear? Sound problem? Ronik, कुछ आवाज का issue है क्या? I think it's fine, right? Please type in the chat box. Any sound issue? It is good, sir. Okay. Ronik, I think आपके सिस्टम में कुछ issue था. एक बार थोड़ा refresh कीजिए, ठीक है? क्योंकि सारे लोगों का किसी को problem नहीं है. So please continue. Fine. So let us see this. The air inside a space capsule is maintained at the required condition by passing it to a set of heat exchangers. Okay. So basically क्या होता है? हमारे पास कुछ heat exchangers हैं, and we are actually sending in some air, and it is coming out. This is in and this is out, and they are heat exchangers. Normally we denote these heat exchangers something like this. So heat exchangers is this. The heat exchangers are designed such that the humid air, what is the meaning of humid air? Normally water vapor will be there, passes through them, is cooled and partial condensation of the water vapor occurs. These terms are very important. Look, this is humid air, first of all, whichever is flowing is humid air, is passing through the heat exchanger coils. It is cooled. So पहले air का temperature नीचे आएगा and partial condensation of the water vapor occurs. So मान लो कि आपके पास कुछ air है and उससे हम water condense कर रहे हैं. Okay, then what happens to the water content in the air actually? Normally if you take air, what happens? There is water in air. If you want proof, take a cooling bottle out of the fridge and leave it in the room, then definitely you can see small water particles will land on the surface of the water bottle. From where this water is coming? From the surrounding air actually. Okay, so practically in air you will have water in superheated state. Okay, when you take this cool atmosphere, like you take a cool bottle for example, मान लो कि आपके पास एक cooling bottle था, so if you clean this bottle completely, it is filled with cooling water, and if you keep it in a room like this, then after some time you will find there is lot of water droplets on this, correct? So from where this water is coming actually, because atmospheric air में कुछ पानी है, and that water is actually present in the saturated vapor, superheated vapor state. Okay, and when you cool this bottle, then definitely what happens? This at some particular point, the temperature of the air falls below the dew point temperature, and they start forming this dew points or water particles on the top of the bottle actually here. Okay, so that's why in that case we'll see that's called dehumidification generally, because you will take out the water. Now let us see on a psychrometric chart. This process appears as a line which is horizontal to the left, vertically downwards, diagonally downwards to the left, diagonal upwards to the right. So first of all, if you see the psychrometric chart, so psychrometric chart will be something like this, correct? So this is omega, which is specific humidity, and also if you see, this is your psychrometric chart, and here you have the dye bulb temperature in degrees Celsius, correct? And now you have constant humidity, this relative humidity lines, something like this, and this is 100% saturated case. Okay, now try to understand this. Fine, forget about this relative humidity lines as of now. So this is omega, which denotes mass of vapor by total mass actually here in a given sample of moist air. So they are telling you moist air is passing through the heat exchanger. Now by the time it is coming out, air is getting cooled. First of all, when air is getting cooled, temperature, the dye bulb temperature, should it decrease or should it increase? Let us suppose if this is the initial state of the air, it has some amount of water vapor and it is also at some temperature. Now tell me one thing, this point is here. Whenever you are cooling the air, the temperature of the air should come down or it should increase. Type in the chat box. What should happen to the temperature of the air in that case? It should increase or it should decrease? It should decrease, correct? So some temperature should decrease. And also partial condensation of water vapor occurs. So partial condensation. So what is the meaning of partial condensation? From that air which is available, you are taking out some water, correct? So from the air, if you are taking out some water, what's happening to the water content in the air? That also decreases, correct? Because you are doing condensation, and जो air में पानी होते हैं, so उस पानी को हम निकालते हैं partial condensation से. So therefore you can see this omega value should also decrease. मतलब the finishing point should be below this horizontal line, and also it should be to the left of this horizontal line. So it should be somewhere here. Okay, so this point should be somewhere here actually, and they told it is a straight line, so that's why this straight line should be something like this. This is state 1, this is state 2, and this should be the line actually here. क्योंकि cooling and dehumidification बोलते हैं इसको, cooling and dehumidification, cooling and dehumidification. Okay, dehumidification क्यों? क्योंकि we are condensing the water vapor. अगर आपने कुछ condensation किया तो this mass of vapor inside the total air will decrease in that case. Okay, so that's why cooling and dehumidification is something like the arrow towards left in this case. Okay, and bottom of course. Okay, so diagonal towards to the left. Option C is the correct answer in this case. Clear? So clear to everyone? So please type in the chat box. Is this clear to all of you? Yes or no? So please type in the chat box. Is this clear to every one of you? This value is nothing. This basically see dehumidification. So how can we say it would be a straight line? Because in the question it is given. That's it. Okay. Is this clear to all of you? Did you understand why it's a straight line? Because it is directly given in the question. And normally in this case, if you look at these things like specific volume, basically it can be any process, but normally we denote this cooling and dehumidification with this lines actually. Okay, that depends upon the complete the substance which we are cooling, the type of the gas what we are cooling and all. Okay, because it is clearly given in the question as a line. That's why all these four options are lines. So that's why this is a diagonal towards the left bottom. Okay, so now I thought of giving you one very important thing again. Basically, acoustic velocity. So what is this acoustic velocity? When you are dealing with ISRO exam, especially with compressible flows, this question comes many times in exam. Okay, so let us see what is the acoustic velocity. So I have just given you some idea. Basically, this is also one clipping from my class notes actually. But since this concept is very much important for ISRO, and every year you see some questions based on acoustic velocity, Mach number, or compressible effects. So that's why I'm giving this, slides here. So we will do a bit of analysis. Basically, acoustic velocity is if you create a disturbance in the medium, then the disturbance will move with some velocity. So here you see this disturbance is this wave front what I have created. Okay, so this is the disturbance which is traveling at some acoustic velocity A, and this velocity of the disturbance in a medium is called acoustic velocity. So we will have a lot of examples and understandings at this point. I have to talk about the wave front. Okay, normally this is called the wave front. Then I'll take this as a control volume. Then we will do some steady flow energy equation analysis, some bit of explanations and all. But right now I'm not doing that because we have a very short session and हमारे पास बहुत सारे questions भी है solve करने के लिए. So I'm just going directly. Okay, but this content will be available in your PDF if you see. So when you apply the steady flow energy equation to this control volume, we will understand certain things here. There is piston is given a small velocity displacement dV, because of which a disturbance got created, and this disturbance will be moving at some velocity A. Actually, this A is called acoustic velocity, and this small h is enthalpy, pressure, density, and there is some changes in the left of this control volume because this region is already disturbed by this control volume. So that's why there is some change in properties. Now when you apply the steady flow conditions, mass conservation basically, okay, so when you apply mass conservation you will get some relation. When you apply energy conservation, again you will get some relation actually. So this is the second equation from TDS equations. After comparing and all, you will come to know that acoustic velocity is equal to adiabatic modulus dP by dO at adiabatic conditions. And for adiabatic process, after finding out something, we will know that dP by dO at adiabatic conditions is gamma P by O. And finally, this is the expression for calculating the acoustic velocity, and this formula is very, very important because many times questions directly come from this formula, and also previously when a question solved here, A is equal to root gamma RT. So this is the formula what I have used here. Okay, so square root of gamma P by O, root gamma RT, root, and this R can be written as universal gas constant by molecular weight. So all these things will be coming under this case actually. Okay, so at the end of this session, can you tell me about the ISRO batch? Like, will it be more questions based or just TI? Yes, definitely I'll give you some details on ISRO batch. Why is this unclear? अच्छा, लेकिन I think कुछ लोगों के पास इस issue था, लेकिन normally बहुत सारे लोगों को आवाज ठीक से आ रही है. Okay, so please go through this understanding once. It will be easily understandable. You can say I have given every simple definitions here and there, every simple calculations what I have done in each step. So everything will be in detail. So please go through this PDF once, and this will be only some 5 slides. 1, 2, 3, 4, 5. Okay, so you can easily understand this expression, how this is coming. Okay, even if you don't understand, please if you don't look at this, so please make sure one thing, that J is equal to root gamma RT whenever there is passing through some ideal gas, and this is also gamma P by rho, or this is adiabatic dP by dO value actually. Okay, bulk modulus. So we see a lot of things, and Mach number is basically actual velocity of the body in a given medium by acoustic velocity. Okay, so this is one very important understanding here. Okay, so finally this acoustic velocity derivation and Mach number आपको ये PDF मिलेगा. So ये PDF से आप एक बार इस 4 slides या 5 slides को एक बार देख लीजिए. ठीक है? So right now we are just solving some questions on this. So let us go forward here. Okay, so this is some content. Again, I thought of putting it here because there will be at least one question based on this complete story of acoustic velocity or Mach number every year in ISRO exam. Okay, a house refrigerator with its door open is switched on in a closed room. The air in the room is dash. One of the very, very standard questions that we discussed during first law of thermodynamics. Okay, so मान लो कि आपके पास room and also there is a refrigerator inside. There is a refrigerator at this corner of the room, for example. Okay, and let us suppose if there is heater coils here, this condenser coils, for example here. Okay, normally if you see the back side of the fridge, you will have some coils like this. So those are the condenser coils. Okay, now a house refrigerator with its door open is switched on in a closed room actually here. Okay, so this room is closed, and generally it should be insulated. Otherwise you cannot decide. So this should be insulated, but when they told closed room, that means air is not entering. So this room is at some steady state condition with some insulation. Okay, normally if they don't mention this word insulation, you cannot tell heated. Okay, because you can see whatever the heat is ejected by this heat engine, some heat might have got out actually here through these walls. Okay, so through conduction to the walls, it can escape. But actually this room is given, it's a closed room. So practically they mean that no amount of energy interactions or mass interactions is taking place. Okay, so that's right. Now whenever you see, if you apply there will be some electric supply which is coming to this refrigerator, yes or no? So there is some energy input, and practically when this is insulated, nothing is going out, so E in minus E out will be equal to delta E of the system. And here you can see nothing is going out, definitely delta E of the system means even though this refrigerator is doing its work cooling, but this condenser coils will add the heat into the room actually, okay? So because of which the room temperature gets heated. Never feel that in a closed room if you open the refrigerator and if you go, by the time you come back, room will get cooled, okay? Don't do this because room will actually get heated up. If the room don't have a proper ventilation, if this heat cannot get transferred outside, so definitely room air ka temperature badega, okay? And also don't do this mistake, like many people feel this, if you put on the fan and if you go out, then the room will again come down. No, even in that case you will feel very hotness in the room after you come back. The reason is the same thing. Energy will be coming in terms of electrical energy, but no energy will be going out. So definitely the energy of the system which is inside, normally the atmospheric air, will increase, okay? So that's why this is very dangerous. So don't do these kind of things by expecting some cooling to happen. Definitely actually heating happens, okay, instead of cooling. Then you have to pay the power bill and also have to have some discomfort, okay? So that's why this normally the temperature will be there and the air in the room will get heated because of this understanding. Delta E is positive in this case, okay, because this value is positive and this value is also positive then, definitely, okay? So this implies normally if you take air as ideal gas, this change in energy of the system is nothing but mass into Cv into dt. This is also positive. Since these two guys are positive, delta T is positive. So definitely the temperature in the room will increase. That means the air actually gets heated, which is inside the room actually here, okay? So this is one common misunderstanding in many students, and that's the reason why this is one of the famous interview questions. People will feel that whatever the heat is in the room, that will be actually sent into the refrigerator and room gets cooled, but actually this condenser coils will again eject that heat into the room, and finally you will experience after some time the room gets heated up, okay? Is this clear to all of you? So please type in the chat box. Is this clear to everyone? Okay. Chalo. I have a question actually. I want to ask you this question, not this question. एक इंटरव्यू क्वेश्चन था मेरे पास, ओके? नॉर्मली मान लो कि मेरे पास एक चैनल और एक क्रॉस सेक्शन था एंड आई वांट टू इंक्रीज द वेलोसिटी ऑफ द एयर इन दैट क्रॉस सेक्शन, ओके, और इंक्रीज द वेलोसिटी ऑफ द सिस्टम व्हिच इज फ्लोइंग थ्रू द क्रॉस सेक्शन. देन टेल मी, अगर मैं वेलोसिटी बढ़ना है तो क्रॉस सेक्शन कन्वर्ज बनाना है या डाइवर्जिंग बनाना है? आई वांट टू एक्सेलरेट द फ्लूइड, ओके? सो मेरे पास एक क्रॉस सेक्शन था एंड एक ट्यूब और समथिंग लाइक दैट. सो आई एम सेंडिंग इन सम एयर. सो मान लो कि मैं अगर फ्लूइड को एक्सेलरेटिंग करना है, ओके, एक्सेलरेट करना है, देन व्हाट शुड बी माय क्रॉस सेक्शन? इट शुड बी कन्वर्जिंग और डाइवर्जिंग? What should be the cross section actually in that case? Converging or diverging? Converging or diverging? Come on, quick. Converging, correct? Many of you told it is converging. Okay, it is converging. Great. Look, converging, fine. Let me tell you one thing. कभी रॉकेट्स देखा आपने? अगर कुछ रॉकेट्स का इमेजेस देखा तो they will be in this shape. These are the side thrusters. क्योंकि हम इसरो का PYQs डिस्कस कर रहे हैं, सो कुछ प्रैक्टिकल भी होना चाहिए, ठीक है? नॉर्मली दिस इज द केस. आप लोगों को पता है कि रॉकेट न्यूटन थर्ड लॉ ऑफ मोशन से चलेगा, मतलब डिपेंडिंग ऑन द थ्रस्ट वेलोसिटी द फोर्स ऑन द रॉकेट विल बी देयर F, एंड दिस साइड थ्रस्टर्स विल आल्सो हेल्प ऑब्वियसली. सो देयर इज सम फोर्स व्हिच इज इन द अपवर्ड डायरेक्शन. सो मान लो कि अगर आपके रॉकेट पे फोर्स ज्यादा होना चाहिए तो this exit velocity भी ज्यादा होना चाहिए, correct? Because if this exit velocity is VE and if this is force F, then as per Newton's third law of motion, अगर आपकी exit velocity बहुत ज्यादा है तो so force भी ज्यादा है. And if you see, if you want to have this velocity increasing, okay, if this velocity has to be more, that means fluid acceleration has to be more, correct? Now, if fluid acceleration has to be more, as per your chat box answers, this passage should be converging. लेकिन आपने देखा कि सारे रॉकेट्स का exit thrusters डाइवर्जिंग होते हैं. क्यों? एनी आइडिया? प्रैक्टिकली एज पर योर अंडरस्टैंडिंग, अगर फ्लूइड का वेलोसिटी एक्सेलरेट मतलब बढ़ना है तो कन्वर्जिंग, हम पासेस को कन्वर्जिंग बनाना चाहिए, लेकिन सारे चीजों को यहां देखा तो डाइवर्जिंग होते हैं. क्यों? मैक नंबर इज लेस देन 1 इज रिक्वायर्ड condition in converging. Excellent Satyajit. Look, I'll explain you this condition. Basically मैंने कुछ explanation दिया जब fluid mechanics का क्लास था उस टाइम पे एक्सप्लेनेशन दिया. नॉर्मली दिस इज द टाइप ऑफ फ्लोज दैट वी डिस्कस. ओके, फ्लोज विद, बिकॉज अभी मैंने आपको मैक नंबर का डेफिनेशन पढ़ाया, सो इसलिए आई एम टेलिंग यू मैक लेस देन 1 इज कॉल्ड सबसोनिक फ्लो, एंड व्हेनेवर मैक इज इक्वल टू 1 ऑलमोस्ट, दैट फेस इज वेरी वेरी डेंजरस इन मूवमेंट ऑफ एनीथिंग, बिकॉज आई हैव स्टार्टेड पीएचडी इन कंबशन एक्चुअली बट लेटर left it. Okay, but during that time I have learned a lot on combustion. So these velocities are called subsonic, transonic, supersonic and hypersonic. Normally in hypersonic missiles and all, when we talk about the things, the combustion, the flows will be within this range. Okay, and normally at normal conditions, whenever the air is at 27 degrees Celsius, उस time पे acoustic velocity इतना होता है 347 meters around. Okay, so square root of gamma t for gamma of air 1.4, characteristic gas constant 287 joule per kg Kelvin, temperature 300. So this will be around 347.12. So आपने अगर एक हाइपरसोनिक मिसाइल लिया तो मास मैक वैल्यू इज इक्वल टू 6, सो 2.1 किलोमीटर पर सेकंड. लेकिन आपने कुछ एनालिसिस देखा तो हियर वन डायमेंशनल आइसेंट्रोपिक फ्लो. मान लो कि एक ऐसा एक क्रॉस सेक्शन था, दिस इज A1, दिस इज A2. ओके, सो इफ दिस इज A1 and if this is A2, by applying mass conservation and also by applying this energy conservation, again you will end up with some things where you will get this relation finally. Okay, it's a very simple relation, mass conservation and energy conservation, that's it. You have to apply these two things, mass conservation and also this is energy conservation. Okay, now when you apply this energy conservation, you will get this equation. So as per this equation you can understand one thing, अगर आपकी फ्लो मैक नंबर से 1 है तो मतलब आपकी फ्लो सबसोनिक है तो so मैक नंबर is less than 1. So मान लो कि whenever Mach number is less than 1, I have done the analysis here. If Mach number is less than 1, this complete quantity on the right hand side minus A by V 1 minus Mach square will be 0. Yes or no? Because when Mach is less than 1, this value will be positive, and because of this negative sign, this total value will be negative. dA by dV is negative if Mach number is actually less than 1. So मतलब क्या होता है? If dA is positive, dV will be negative, correct? Because this ratio dA by dV has to be negative. So that's why if dA is positive, dV should be negative. That means, or if dV is positive, dA should be negative. dV is positive means if you have a cross section V1 and V2, if V2 has to be more than V1, if difference final minus initial has to be positive, that means if V2 is more than V1, if the fluid has to be accelerating, this dA should be negative, means final cross section should be less than the initial cross section. So the passages should be converging in that case. Okay, so for Mach numbers less than 1, this passage has to be converging like this, and for Mach number more than 1, this should be diverging like in the practical case. Okay, so therefore the rocket initially it starts its motion, it will very soon reaches its, the rocket will very soon, just a minute, yeah, somewhere here we have some questions. Fine. So the rocket will very soon reaches its Mach scale. Okay. So whenever it reaches Mach is equal to 1, then immediately for further thrust you have to have diverging nozzles. So immediately, so generally if you see these nozzles, I'll show you rocket nozzles. You can see. I'll show you some bit here. So you can see here these nozzles. Normally, yeah, you can see. This is converging only for the initial part, but later much it is diverging part actually. So the engines will be diverging in practical case. Okay, you can see any model. So anyhow, those are the practical engines. You can see in all these engines, you can see flame is there in this beautifully. There's a test going on, engine test that is going on here. So normal shocks and all. So basically these are the diverging cross sections. Okay, because of this understanding. Clear? So ISRO PYQs का है ना, so कुछ interesting चीज भी पढ़ाना चाहिए. So इसलिए I've kept all these points. Fine. Are you all comfortable with my Hindi? At least understandable? Or it's looking very bad? Because I have started speaking only 5-6 months back, so I think it should be good. So what happens when reaching Mach number is equal to 1? That's the most critical case. Okay. Normally you have two types of shocks, which are called normal shocks and oblique shocks, which we generally study if you do a course on compressible flows actually. So normal shock एक होता है, normally valley flow, all these cases are there, but generally we don't discuss that right now. But if you have some understanding, then if you have some interest, I would like to go. I would refer you something like compressible flows by there's an NPTEL course where you can go for some 2-3 lectures by IIT Madras. This ma'am, I forgot her name, Rinku Mukherjee. Okay, so she's from Applied Mechanics department, and she has done one beautiful course on compressible flows because I have attended under one elective under her. So at that time. मैम ने बहुत अच्छी तरह से पढ़ाया था उस टाइम पे. ओके, माय हिंदी इज गुड, सो एटलीस्ट अंडरस्टैंडेबल, थैंक गॉड. ओके, क्योंकि 6 महीने पहले जब मैंने पीडब्ल्यू ज्वाइन हुआ उस टाइम पे मैंने आई यूज्ड टू से इन यूट्यूब सेशंस लाइक 6 महीने के बाद मैं हिंदी में क्लासेस लेता हूँ. सो लेकिन अभी इट्स बीन ऑलरेडी सम 6-7 months आई थिंक, सो आई हैव टू स्टार्ट स्पीकिंग इन हिंदी. एंड जब मैं आगे लाते हैं उस टाइम पे आई विल do much better in make you guys understand my Hindi. Okay, fine. So let us solve this question. The working temperatures in evaporator and condenser coils of a refrigerator are minus 25 degrees Celsius and 30 degrees Celsius respectively. So basically this is the heat addition temperature to the refrigeration cycle and this is the heat rejection temperature. Okay, the COP of the refrigerator is 0.85 of the maximum COP for a power input of 2 kilowatts. The refrigeration effect produced will be dash. Okay, so they have given you some options again. So let us do this. हमारे पास एक रेफ्रिजरेशन साइकिल था. सो वी हैव ए रेफ्रिजरेशन साइकिल. देन दिस इज टेकिंग हीट, मींस बेसिकली द एवापोरेटर कॉइल्स. हैव यू एवर सीन वेयर विल बी द एवापोरेटर कॉइल्स इन योर फ्रिज? देखा कभी? मान लो कि ये आपका फ्रिज है. किसको पता है कि इस पूरे वॉल्यूम पे where we have this evaporator coils actually? Do you know where you get this? I'll write 3 phases. 1, 2, 3. Okay, I'm talking about the back. Okay, this is the back view of the phase, not the front view, because in front view you have a door here. Okay, so forget about that. Anyhow the evaporator coils won't be in the door because that is disconnecting. Okay, so that's why out of these 2 phases, this is the back phase, top phase and side phase. Do you know where will be the evaporator coils actually? On the diffuser, on the top basically. Okay, so here you will have the evaporator coils actually in the phase. Don't tell that sir हमारे घर पे एक अच्छा क्लॉथ था, coils नहीं है. Okay, but actually if you cut, मतलब don't tie in your home, but if you go to some service center you can see there will be some evaporator coils here. ठीक है? So there will be, yes, it is the first phase. There will be some evaporator coils and these evaporator coils will pick the heat from the refrigerator space. That's why the top will be generally the diffuser location. Because of buoyancy also hot air will flow up, so that's why cooling becomes very easy. Okay, this is also one interview questions. Why you can see there is a diffuser at the top in most of the phases actually. Okay, the reason is this is actually most cost effective and also performance effective actually, because I'll tell you, when you keep some hot bodies inside, let us suppose you keep some food or something like this, some milk or whatever, these guys will release some heat into the air inside the refrigerator. So we know by buoyancy hot air will be less will be having less density as compared to the cold air. So that's why when this air gets hotted up, this air will try to move. So that's why these coils will be always on the top, so that the heat picking will become easy for the refrigerant gas actually. Okay, so that's why we actually want a refrigerator like this. So fine, anyway, so let us see this evaporator coils at minus 25 degrees Celsius. So what is the meaning of minus 25 degrees Celsius? 273 minus 25. So this gives you 248 actually. Okay, so 248 Kelvin. And what about the heat ejection temperature? So this is 30 degrees, so 303 Kelvin. 273, so 330. Now if you see, there is some QL, QH, and there is some work input to the compressor. Now this is Q dot H, Q dot L, and W dot input to the compressor. Okay. Now they are telling you COP of this is 0.85 times the maximum COP for a power plant. Okay, maximum COP. So basically here COP actual is 0.85 times of maximum COP. So maximum COP will be there for a reversible refrigerator. Yes or no? If your COP has to be maximum, this refrigerator should operate under ideal conditions. Okay, means the reversible conditions. So therefore COP of actual refrigerator is equal to 0.85 times of, and actual refrigerator का COP क्या होता है? So this is TL and this is TH. So TL divided by इन दोनों का बीच में डिफरेंस कितना है? So 30 and 25. So 55 is the difference actually. So 248 by 55 ये होता है कि actual reversible COP, लेकिन actual COP कितना है? इससे 85% है. So 0.85 हम मल्टीप्लाई करना है इससे. Okay, so 0.85 into 248 by 55. Now let us see the refrigeration effect produced, मतलब Q dot L का वैल्यू कितना है ये पूछा है हम क्वेश्चन में, and W dot power input to the compressor is 2 kilowatts. So this is 2 kilowatts. So COP का एक्चुअल डेफिनेशन क्या होते हैं? COP is equal to Q dot L, effusion effect, divided by W dot. So this is equal to 0.85 times of that value. So 0.85 times of 248 by 55 actually. So this is the difference. Okay, so this is the difference actually. Now if you simplify this, Q dot L, so this value Q dot L is equal to work input to the compressor 2 kilowatt. So 2 into 0.85, let us suppose 85 by 100 into 248 by 55 actually here. Okay, so this is 55. Okay, so this is 55. Now if you simplify this, 11, and also this is, this is around 13 I guess, right? 5 13s are 65, so 17. This is 17. 5 17s are 85 actually. Okay, and 11, you have this 11 actually. So 2 table 22 times 44, 4.5 around. Okay, so this is 0.5 around. So 2 times of 24.5 around 49. So 49 into 70 by 100. So 49 into 70 by 100. So 49 into 17 by 100 almost. So if you see, this is almost around 2. So if this is almost 2, then this will be almost around 8, close to 8. So some value which is close to 8, 7.6. So this 7.6 kilowatts is what you can take. Okay, because ISRO के एग्जाम पे कैलकुलेटर अलाउ नहीं करते हैं, so इसलिए हम कैलकुलेशंस मैन्युअली करना पड़ेगा. एंड इवन दिस टाइम आई एम थिंकिंग कैलकुलेटर इज नॉट अलाउड, क्योंकि वो लोग ने इस बार एग्जाम का फॉर्मेट थोड़ा चेंज किया. लास्ट टाइम तक फॉर्मेट ये होता है कि टोटल 90 क्वेश्चंस एंड उस 90 क्वेश्चंस में 80 क्वेश्चंस एक्चुअली. सो 80 क्वेश्चंस और 90 मिनट्स दिया, लेकिन इस बार एप्टीट्यूड भी इंक्लूड किया था एग्जाम पे. ओके, अगर कुछ एग्जाम में एप्टीट्यूड है तो नॉर्मली बिना गेट एग्जाम, ओके, इफ यू लीव द गेट एग्जाम एंड इफ यू थिंक किस एग्जाम में एप्टीट्यूड होते हैं, उन एग्जाम पे कैलकुलेटर का अलाउ नहीं करते हैं जनरली. सो इवन दिस टाइम वी आर एक्सपेक्टिंग दैट दे डोंट अलाउ द कैलकुलेटर. ओके, सो 7.6 kilowatts is the calculation that you get actually here. 2 into 17 into this is around 22. This is 22.5, sorry. Okay, so 22.5, something around that. And so if you multiply the calculations, then that comes something less than 8. So if you see the options, there is only one option which is less than 8. So 7.6 kilowatts is the correct answer. It's not like you have to do the actual division and all. Just by the idea what you have in the calculations, just compare the values and look for the options. And यहाँ options के बीच में बहुत gap भी था. This is less than 8. All these options are more than 8. Okay, and if you cancel this 11, 22.5 तक आएगा. So 2 into 22.5 around 45 by 100. So 45 by 100. So value should be less than 8.5 definitely. Okay, so there is only one option. That's how you can decide it is 7.6. लेकिन process, is this clear to all of you? Process सबको समझ में आएगा? So please type in the chat box. Yes. क्योंकि गेट एग्जाम पे कैलकुलेटर नहीं करते. ओके, सो यू हैव टू डू द कैलकुलेशंस मैन्युअली. लेकिन कैलकुलेशंस भी बहुत सिंपल रहते हैं. यू नीड नॉट डू वेरी मच कैलकुलेशंस लाइक लॉगरिथम्स, एक्सपोनेंशियल्स. दीस कैलकुलेशंस वोंट बी देयर. बहुत सारे सिंपल कैलकुलेशंस, मल्टीप्लिकेशंस, डिविजन्स होते हैं. ओके, आप बाकी सब्जेक्ट्स में भी देखा तो आपको इजीली पता चलेगा कि कैलकुलेशन बहुत आसान मिलेगा. नेक्स्ट, लेट अस सॉल्व दिस क्वेश्चन. An engine works on Carnot cycle between 727 and 227 degrees Celsius. The efficiency of the engine. बहुत सारे simple question था. Thermal efficiency is equal to 1 minus lower temperature by higher temperature of heat ejection. So 1 minus 227 plus 273. 500, 727 plus 273 is 1000. Okay, so if you simplify this, 50% actually here. That's it. Okay, very simple question. 227 degrees Celsius is how much? Plus 273. If you add, this will be 500. Okay, and similarly, इसको भी 273 add किया तो 1000 Kelvin. So heat ejection is at 500 Kelvin, heat addition is at 1000 Kelvin. So efficiency कितना होता है? एक Carnot इंजन है, इसमें दिया था Carnot cycle. So अगर इस इंजन Carnot cycle से काम किया तो efficiency is equal to 1 minus TL by TH. So 1 minus 500 by 1000. So 50%. Simple calculation. Option A is the correct answer. Okay, 2016 के टाइम पे आया था इस क्वेश्चन. Okay, clear to all of you? So please type in the chat box. Okay. Then let us see this question. A steam thermal power plant works on. बताइए आंसर क्या है इसका? What is the cycle on which the steam power plant operates? Steam power plant, steam thermal power plant, of course. Yes, this operates on Rankine cycle. Correct. So this operates on Rankine cycle. So basically, if you see, this is steam power plants. Or sometimes we call that vapor power plants also. But normally we use steam. That's why we have a lot of hydroelectric power plants actually. And Brayton cycle में gas power cycles. Normally we have worked on this in GTGs and all. Of course, this is not the correct answer for this question, but gas power cycles is on this. Normally on Carnot cycle, ideally no device actually operates in reality on Carnot cycle, of course, but under certain special considerations, like for example, if you increase the stages of compression and expansion to very large number of compressions and expansions in Brayton cycle, that get converted to Carnot cycle. But the work output drastically reduces, so that's why we do not do the Carnot efficiency. In Otto cycle, all the SI engines generally, spark ignition engines, they actually operate on this. Okay, so we have the Rankine cycle in this case. Rankine cycle में बहुत important एक interview question है. Shall we discuss that? 2-3 मिनट लगेगा उसमें बस. Okay. Both important interview question and also one of the most frequent interview question in many interviews related to Rankine cycle. Okay, सिर्फ 2-3 मिनट स्पेंड करेंगे उसमें. Yes, okay. So आपने अगर TS डायग्राम बनाया तो TS, you have this pump do some work, then you have constant pressure, heat addition, then there is a turbine in which you expand generally. Look, this is heat addition, then this is expansion, and this is a condenser. आप सबको पता है 1, 2, 3, 4 normally 4 devices, एक पंप होता है, एक बॉयलर, एंड बॉयलर से टर्बाइन में आते हैं, एंड दिस इज कंडेंसर. नाउ मान लो कि हमारे पास कंडेंसर नहीं है. ओके, सो मान लो कि हमारे पास एक कंडेंसर नहीं है, क्योंकि कंडेंसर का काम क्या है? दिस स्टीम विल कम आउट एट द मोस्ट what do you say, this saturated, generally it is very close to saturated vapor. Dense fraction बहुत ज्यादा होते हैं, 0.9, 0.85 to 0.95 के बीच में होते हैं generally, and this condenser will just reject heat and it's a phase change, correct? So sound glitching, कुछ sound glitching है क्या? एक मिनट, हमारा स्टूडियो टीम बंदे भी कॉल करे, नहीं? No, ठीक है. साउंड का इश्यू है क्या? कुछ सब ठीक से चल रहा है ना? कोई इश्यू है? नॉर्मल की नो सर. अच्छा, लेकिन मेरे सिस्टम से बहुत क्लियर है सारी चीज, सारे डिवाइसेस. हाँ सर, एको है बट इट्स नॉर्मल. एको है, एक मिनट मैं कंफर्म करता हूं अगर एको है तो. ठीक है, अब बोलिए, अब बताइए, अभी भी एको आए? अभी भी एको आए? परफेक्ट, राइट, गेट. ठीक है, मैं स्टूडियो इंजीनियर भी बन सकता हूं. ओके, गेट. जब बहुत सारी बार थर्मोडायनेमिक्स, फ्लूइड मैकेनिक्स, हीट ट्रांसफर, स्ट्रेंथ ऑफ मेटल्स, मैथ्स, ये सब पढ़ने के बाद बहुत व्हाट डू यू से, लाइक द सेम थिंग फैटिग आए. सो इसलिए मैंने कुछ दिन स्टूडियो में भी काम करते हैं. ओके, कुछ टेक्निकल इश्यूज से सॉल्व करते हैं बेटर. ओके, क्योंकि अब हमको एक्सपीरियंस भी आया, कुछ एको रिड्यूस किया अभी. ओके, फाइन. सो लेट अस सी हियर. नाउ द मेन क्वेश्चन इन इंटरव्यूज अबाउट दिस रैंकिन साइकिल इज why you have to have a condenser mandatorily. Okay, because अगर कंडेंसर नहीं है तो क्या होते हैं? मान लो कि हमारे पास एक पंप है. Look, I'm discussing this question actually. कुछ स्पेस है ना? ठीक है, मैं यहाँ डिस्कस करता हूँ. नॉर्मली रैंकिन साइकिल में एक पंप होते हैं हमारे पास. इस पंप से बॉयलर में फ्लूइड जाते हैं, एंड देन इस बॉयलर से टर्बाइन में फ्लूइड आते हैं. सो कुछ शाफ्ट वर्क मिलेगा हमको, एंड फाइनली इन दोनों चीज़ों को एक कंडेंसर कनेक्ट करते हैं, है ना? एक कंडेंसर कनेक्ट करते हैं इन सारी चीज़ों को. मान लो कि हमारे पास कंडेंसर बहुत कॉस्टली है. सो मान लो कि हमारे पास एक फ्रेश वाटर का लेक है. ओके, सो एक फ्रेश वाटर का लेक है. सो आई एम रिमूविंग दिस कंडेंसर, एंड मान लो कि हमारे पास एक लार्ज लेक है हमारे पास. सो लेट अस सपोज यू आर टेकिंग वाटर डायरेक्टली फ्रॉम दैट lake. It's a very large lake. Okay, whatever the water you take, whatever the heat you put, the properties of this water does not change. Okay, there's a large lake available. It's a fresh water lake. Normally when we take this water, many of you may say that because of some impurities, salts and all, some scaling on pumps, boiler will get damaged and all. But let us suppose it's a very large fresh water lake. But if you have this large fresh water lake, you can take water directly to pump from this reservoir, and also you can eject the turbine output. Then no need of compressor actually. Then you can save the cost of a this condenser actually. Okay, then why you cannot run a plant like this? Or first of all tell me, can you run a plant like this? without having the condenser? Without having the condenser, can you run a plant like this? A Rankine cycle, basically. Taking water from the fresh water lake and rejecting it to the same location. This can actually solve your purpose because टर्बाइन रन करने के लिए कुछ स्टीम होना चाहिए एंड स्टीम मैन्युफैक्चरिंग करने के लिए पंप है बस. Now tell me, is this condenser mandatory in a pump, in a Rankine cycle actually? So please take some sessions on interview like this. We'll discuss. Okay, पहले हम एग्जाम क्लियर करते हैं, उसके बाद इंटरव्यू के सेशंस लेते हैं, ठीक है? So but tell me one thing, can without this condenser can this Rankine cycle operate? More heat would be required every time. No. Why? Because you see same water almost here, pump is actually pressurizing and pump work will be very small क्योंकि हम सारे लोगों को पता है कि control volume work is equal to minus integral VdP and this is from inlet pressure to outlet pressure. This volume, because pump generally liquids को handle करते हैं, so liquids density will be large, so density of water is around 1000, so specific volume will be 0.001. normally pump works बहुत कम होते हैं, okay? so इसलिए जब हम इस Rankine cycle का thermodynamic analysis करते हैं उस टाइम पे हम pump का work neglect करते हैं क्योंकि इस specific volume बहुत कम है actually, okay? and if you want to run the pump, actually pump will be generally taken from the electrical supply. You might have seen pump houses. I'll show you this pump houses also. Normally when I was in refinery, I was walking out so many pump houses. So pump houses in refineries normally. So I'll show you some images of pump houses. Yes, this is one fantastic image. Yes, you can see basically all these are pump houses actually, okay? You see lot of pumps in a line. These are called pump houses. You'll have a lot of pumps. You see there are a lot of pumps here, okay? and every pump is actually operated by electric motor. You can see motors are clearly visible at some location. Yeah, okay, in this picture also motors are available. You can see if you take this pump for example, if you take this pump, electric motors are connected, okay? So practically what happens, you will run an electric motor, you will run a pump, and these two shafts are actually coupled, okay? So that when you run the electric motor, this motor shaft will run the pump shaft actually, okay? And every case, whenever you see all these are, if you have motors, that means you are running the pumps with the help of electric supplies, but you will never run a compressor with electric supply. Only some small mechanic shops and all, they run compressors under electric supply, but practically in industries you can never operate a compressor with electric supply, okay? Because sir, how many lectures have you completed till now? This is the first and last lecture I'm going to take, okay? Because only I was allotted only applications of thermodynamics. Rest of the subjects our complete team will take, okay? And if you want to contact me at any time, you can follow this Telegram group I'm giving here. https://t.me pw Vinay Sir, capital SIR, okay? You can follow this. You can join this Telegram group if you want some information regarding thermal sciences, or we can be interactive about. Normally I generally can handle mathematics and all the thermal subjects, basically thermofluid, heat transfer, applications of thermodynamics. These kinds of subjects are my interest. So you can follow, you can basically join this Telegram group or PW group, so that you can get in personal touch with me for any help that you feel that I can help you, okay? So that I'll help you out. Okay, I'll keep this here for some time. So if you want, you can join that. https://t.me/pw Vinay Sir. Okay, you can join that. And now if you see, guys, look one thing very importantly. Normally in Rankine cycles, we come to some concept called, but if you send the expanded steam to pump, it won't work because it will violate the Kelvin-Planck statement. We are not sending expanded steam now. This is a large reservoir, so that even if you are releasing some steam which is at very low pressure generally, because already this pressure, this device, if you leave the turbine to the atmosphere, the exit pressure will be the atmospheric pressure, okay? So that's why this, when it's a large lake, this steam will get condensed again because heat will flow from steam to the water, and finally everything will be same. Let us suppose if you take the pump from some different location, input to the pump from some different location, you will get water directly, okay? But the main drawback in this case is, look, you can run a plant, yes, you can operate plant under these conditions, but the fault is your efficiency will fall drastically. The reason is, whenever you operate at condenser, this condenser pressures will be very much low than atmospheric pressures, okay? So that means whenever you are taking the expansion in a turbine, if you use this condition, you are expanding the steam in the turbine from boiler pressure to atmospheric pressure. But here you are expanding the steam from boiler pressure to some pressure which is below the atmospheric pressure. So if you expand in this case, your work output of the turbine will decrease actually. Okay, so that's why that work output of the turbine should not decrease, because pump work is very less. Okay, boiler also you're adding same amount of heat, but your pump work will fall down. So that's why practically you cannot, even though there is a facility to run a plant like this, but without having a compressor, the plant efficiency will fall down very easily. Okay, so that's why plant efficiency has to be maintained. That's why clearly this condenser is kept in the plant. I can also show you mathematically. Thermal efficiency is equal to 1 minus TL by TH. Whenever there is a heat rejection is at constant temperature, but heat addition is at not at constant temperature. That's why we are maintaining something called mean temperature of heat addition. Now whenever you are rejecting at atmosphere, the rejecting heat rejection is at ambient temperature, but at 40 kilopascals or something like that, at a pressure much below the atmospheric pressure, the saturation temperature will be low, so the heat rejection at this temperature will be much small actually. Okay, so that's why this TL will actually increase in this condition. So efficiency of the plant will fall. Also physically, if you want to understand, this work developed by the turbine will fall down, but heat amount what you are supplying remains same. That's why your efficiency will fall actually. Okay, so that's why in vapor power plants exclusively you should always have a condenser. Clear? So that's why they'll ask you sometimes, because condenser is doing nothing except exchanging heat. So what I'll do, I'll maintain a water plant like this. Okay, you can maintain, but your efficiency of the cycle will fall down. Clear? So how much pressure we can decrease in condenser? Normally the condensers will be like operating at, if you see practically 45 kilopascals, 50 kilopascals at that pressure. Okay, at that pressure the saturation temperature of the liquid, or where the heat rejection happens, will be very small. Okay, as compared to the ambient conditions. Clear? Normally the operating conditions of condensers will be around 40, 45, 50, within this range of kilopascals. Okay, and pump work is much small always, you know that. Okay, so pump work will be generally very small. Clear? So let us go for the next question quickly. A simple steam power cycle receives 1 lakh kilojoule per minute as heat transfer from hot combustion gases and rejects 66,000 kilojoule per minute as heat transfer to the environment. Means basically you can see, did I keep an extra slide here? No, I think okay, fine, I'll manage from here. Guys, look, we will solve this question in a good way. A simple steam power plant cycle, receives 1 lakh kilojoule per minute. So let us suppose if you have a power cycle, this is a power cycle, steam power cycle. Okay, fine. This is a steam power cycle, means basically some Rankine cycle, thing like that. So steam power cycle. Now if this is steam power cycle, then this is getting heat, Q dot S is equal to how much heat it is getting? 1 lakh kilojoule per minute. Get 1 lakh kilojoule per minute. Good enough. And how much heat this guy is ejecting? Q dot R is how much? Q dot R is actually equal to 66,000 kilojoule per minute. So this is 66,000 kilojoule per minute. Good enough. Then what they are asking? If the pump work required is 1400 kilojoule per minute, okay, so pump work they have given. So pump work that you need is actually 1400 kilojoule per minute. Good. Then what is the situation? The thermal efficiency of the cycle and the turbine power output generated is. So basically if this is steam power cycle, you know, there is a pump. Then from the pump it is going to a boiler. Guys, I'll tell you one thing. Whenever I do a boiler like this, I feel very funny. Okay, because why funny is actually in industries, whenever you get a boiler leak, okay, let us suppose if there is some leak on the boiler and if steam is blowing out, that is a very serious problem actually. Okay, and boiler is not very simple like a box and writing boiler in that. Okay, boiler will be a very big boilers in general, and they create a lot of defects actually. Some leaks will be there and all. So whenever there is a leak, normally you keep a patch and weld, and then you do the test, radiography test and all, normally for any leaks and all actually. Okay, So why we can't go beyond it? Because work done is increasing now by decreasing pressure below 40 kilopascals, but there is something called vapor pressure for every fluid, and you should not, you should always have liquid. Okay, you should have the state of the matter as liquid in the condenser. Okay, if you decrease the pressure below 40 kilopascals, then practically what happens is, because of some heat transfer from the surroundings and all, practically what happens that normally, let us suppose if below 40 kilopascals, if the temperature is 10 degrees Celsius or 20 degrees Celsius, something like that, then what happens here is, because of that heat flow, there happens some cavitation problem, which you might have studied in fluid mechanics. When pressure of any substance flow below, fall below the vapor pressure, then bubbles start getting formed inside the system. Okay, and these bubbles will form a cavitation problem, and that will block the device completely. Clear? So that's why we cannot go beyond certain limits. Okay, there is a limit actually. Fine. Yes, theoretically you can go up to 10 kilopascals also, but practically there are certain restrictions because of vapor pressure of the fluids actually in exclusive case. Okay, so if you see this boiler, anyway, this funny boiler, then there's a turbine generating some work output, and there is also some condenser. Okay, so these guys are connected in this fashion. So now if you see, so heat is added in this case, heat is rejected in this case, and work is given to the pump actually, and this guy gives us work outside, W dot of the turbine. Now they are asking you cycle efficiency and also the turbine work output. Okay, now let us see what is the cycle efficiency. How do you calculate this cycle efficiency? Thermal efficiency of the cycle is equal to sigma W by Q dot S. Yes or no? Now tell me one thing, but here turbine work is not known to you, then how will you calculate actually this sigma Q? You know from first law of thermodynamics, this sigma W is same as sigma Q actually here in this case. So this can be written as sigma Q divided by Qs. So 1 minus heat ejected by heat supplied actually here. Of course, you keep weights on both the sides. So 1 minus 66,000 divided by 1 lakh, because units are same, both are in kilojoule per minute. So you can do this calculation. So these zeros and these zeros gets cancelled. So 1 minus 0.066. 100 is there, so 0.66. So this gives you 0.34 actually here. Okay, so 0.34 is what you get. So this is almost 34% efficient. So the plant is actually 34% efficient in this case. So let us check for the option where there is 34. Okay, two options you have 34. Fine. Let us calculate the turbine work output. Now if this is 34, 0.34 is equal to W net divided by heat supplied. So this is 1 lakh. So this gives you W net is equal to 34,000 kilowatts or kilojoule per minute actually. Okay, so 34,000 kilojoule per minute. Now from that quantity, this is the W net. So what is the W net actually? Work generated by the turbine minus work consumed in the pump. Yes or no? Because even though turbine is generating some amount of work, some part, of course very little, is consumed by pump actually. So therefore W of the turbine is equal to W net 34,000 kilojoules per minute minus work consumed by the pump. What is the pump work they have given? 1400 kilojoule per minute. 1400. So 34,000 minus 1400 gives 32,600 kilojoule per minute. This is the amount of work which is produced by the turbine actually. Okay, now let us check. They are asking you in watts actually. Okay, so if they ask you in watts, so divided by 1 minute is equal to 60 seconds. Kilowatts, right? So kilowatts, fine. So this is the calculation, 32,600 divided by 60. So let us do this. 6, this zeros gets cancelled. So 6 5s are 32, 6 5s are 30, so you have 26. So 6 4s are 24. If you have 24, 643.33, that's it. Okay, so 543.33 kilowatts is the turbine work which is generated in this case. So 543 is this calculation got 3260 by 6 actually. This is 0.34, 34% efficient. Good. So 0.34 is equal to W net by heat supplied is 1 lakh. So 34,000. So 34,000 is W net. So this is plus actually, sorry. Work developed by the turbine is, yes, this is plus actually, because you can see W net is equal to work output by the turbine minus work output by the pump. So work consumed by the pump. So W turbine is equal to W net plus WP actually here. Okay, so this is plus actually. So if this is plus, then this quantity is something like 35,400. 400 by 60 seconds. So this value is in kilowatts. So let us calculate this value. 0 gets cancelled. 6 5s are 30, then 54, 6 9s are 54 actually. Correct. So 6 5s are 30, 6 9s are 54. Then that's it, 590 kilowatts. Okay, so 590 kilowatts. So if you see 590 kilowatts is here, so definitely this B is the correct answer. Done. Did you understand this calculation? Very simple calculation. Actually, we calculated the efficiency first of all, and once you calculate the efficiency, then we calculated the total work generated by the turbine. And you know, W net is actually work generated by the turbine minus consumed by the pump. So work generated by the turbine is W net plus work sent to the pump actually. So that's why adding this W net to the pump work gives you this total amount of work which is generated by the turbine. But this value is in kilojoules per minute. So if you want to convert that into kilowatts, you convert that minute into 60 seconds. So if you divide this with 60, this minute gets converted to second. So these units are in kilojoules per second, which is kilowatts actually. Okay, and this calculation is 590 kilowatts. Clear to all of you? Clear? So please type in the chat box. Is this clear to all of you? 590 kilowatts of energy is being is generated by the turbine actually. Okay, simple calculations, nothing use of any calculator or anything. That's why since in exam also no calculator is allowed, so that's why I'm solving all the questions without calculator. Okay, but you can see a very clear idea of each and every example. Is this question clear to all of you? The turbine, work generated by the turbine, and also efficiency of the plant. Everyone who is on live, so please type in the chat box clearly. Yes, done, right? Now let us solve this question. If a certain mass of moist air in an airtight vessel is heated to a higher temperature, then what happens to this specific humidity, relative humidity, and relative humidity are the points of interest. So first of all, you see we have taken a airtight vessel, meaning it's a very closed and rigid. Now you have taken some air in this and heated. Okay, so you have taken some air, atmospheric air in this. So you have taken air in this and you have heated this air. First of all, tell me one thing, answer carefully. Because of this heating, will there be any change in the water vapor present in the air? Let us suppose when you have collected some sample of air inside a vessel, then definitely with that air some amount of water vapor might have also got in. But because of this heating, when this vessel is closed vessel, will there be any change in the mass of the water vapor present in this? Will there be any change in the mass of the water vapor present in this air? Is there any chance to escape for the water vapor? No. Correct? There is no change. Also, what about the total mass of the air actually? What about the total mass of the air actually here in this case? Total mass of the air inside this? That also is fixed. So that means omega. If you calculate about omega, let us see. Let us try to draw on a psychometric chart. Your understanding will be much easier. Okay, so if you have this omega, and this is the dye bulb temperature in degrees Celsius, then in that case, because of this heating, your temperature will increase, but omega will not change. Correct? So if you see the process, it is just a sensible heating. This is state 1 and this is state 2. So this is how you have. Now, no change in mass of water vapor, mass of air remains constant. Correct? Obviously, mass of air remains constant. Now if you see, so this is just a case of sensible heating. So whenever you are doing sensible heating, then if you see this relative humidity and this relative humidity, actually definitely this line is close to the saturated curve. So this will be phi 1 and this will be phi 2. So clearly you can understand, because of this heating, phi 1 is greater than phi 2. That means phi actually decreases. Phi decreases, correct? Because this is a case of sensible heating, and in case of sensible heating, practically you can see there is no change in the mass of the water vapor. So W is fixed and total mass of the air is also fixed. So that's why this omega, which is basically the specific humidity of the vapor, is locked. Okay, so specific humidity is fixed actually. So when specific humidity is fixed, there's no change in the specific humidity. Now talking about relative humidity, since the points is going away from this saturated curve, 100% saturated curve, so that's why there is a decrease in the phi. Relative humidity will decrease obviously. Okay, and also you can understand phi is equal to PV by P saturated at that particular temperature. Okay, so that's why when this temperature is increasing, this phi will actually decrease. Okay, so the correct answer is basically it decreases actually. Okay, so option D is the correct answer. Relative humidity will decrease. Clear to all of you? So please type in the chat box, is this clear to all of you? Did you all understand the simple logics? Okay, you see the questions of ISRO, you need not do mathematical analysis, big mathematical analysis like gate questions. Okay, so हर question को हम ऐसे concept से solve करेंगे. ठीक है? Fine. So let's go for the next question. Let us see. Air is accelerated isentopically from 100 meters per second to 300 meters per second in a nozzle. Fine. If the temperature at the inlet is 127 degrees Celsius, the inlet Mach number is dash, characteristic gas constant is 287, specific heat ratio is 1.4. Okay, so let us calculate the inlet Mach number. So if you want to calculate inlet Mach number, हम कैसे calculate करते हैं? देखिए, Mach number is equal to velocity by acoustic velocity. Correct? I have given you this somewhere here. This understanding I have given you somewhere here actually. Just a minute. Yeah. Previously I think. Yes, here you can see Mach number is equal to velocity by acoustic velocity. So this definition is many times important. You have seen so many questions coming on this Mach number. Fine. So now let us see this Mach number by acoustic velocity actually here. So at the inlet of the nozzle, we want to calculate at the inlet. That means inlet velocity by acoustic velocity at the inlet for that conditions. Okay, so let us see what is the temperature at the inlet, 127. So we know this acoustic velocity is equal to square root of gamma r t actually. Okay, so this is the acoustic velocity, gamma square root of gamma r and t actually here. So if you simplify this, A is equal to square root of 1.4 because gamma, they have given you ratio of specific heats is 1.4. This characteristic gas constant 287 joule per kg Kelvin. What's the value they have given? 287. And inlet temperature. So temperature at the inlet is 127 degrees Celsius. So T inlet is equal to 127 degrees Celsius. So plus 273 if you add, this is 400 Kelvin actually. Okay, so this is 400 Kelvin. Now let us see what is the initial velocity. Velocity at the inlet is 100 meters per second. So if you want to calculate Mach number, let us see. Mach is equal to at inlet 100 meters per second divided with this calculation, square root of 1.4 into 287 into 400 actually here. Then you can do one thing, you can cancel this couple of zeros with a 10 here. Okay, and also you can cancel this 4 and you can write a 5 here. So square root of 5 divided with 1.4 times of 287. So what could be this value? You can see 0.24, 0.2442, 0.747, 0.33. Point table 3 actually. You can understand one thing, there is one similarity between the options. Yes, that value is a bit difficult to calculate without calculator, but try to understand there is some simplicity. How come? Oh, I think I have written this 5 under the square root. So 5 by square root of 1.4 87. Okay, so this is 287. Now you see that calculation, this value is something close to 0.25, this is something below 0.5 but close to 0.5, this is slightly more than slightly close to 0.75, this is 1 by 3 almost. Okay, now if you see this value, square root of 287, okay, so 287 square root is almost in between. This 1.4 is almost close to 1.414, so this is like, you know, square root of 2 actually here, and this 287. So if you do that calculation, 287 into 1.4, for example, 4 7s are 28, 2 4 4 is 28, 29 30, 3 11, 287 actually. So 3978, 397.8. So this calculation is around 397.8. So if this value is around 397.8, almost 397.8, then let us suppose if this value is very close to 400, then if it is actually 400, the value would have been 0.25. Yes or no? if this value is 400 actually, so this value is 400, then 5 by 400 gives you square root of 400 is 20, 5 by 20 is 1 by 4, so 0.25. Yes or no? So answer should be very, very close to 0.25 actually. Clear? So if you see, out of all these options, this is the option which is close to point that. So that's why performing that calculation could give you around 0.249. That is the most appropriate answer out of these 4 options. Did you understand the logic here without calculator? When you calculate this value, 397.8 is what you are getting here. Okay, 397.8. Yeah. So if this is 397.8, then that value is very close to 400. So if that value is very close to 400, this value would have been 0.25 actually. So we have to go for a value which is very close to 0.25, and pehla option EMA 0.249 is there. So that's why we can tick that option actually. So 0.249 is actually the correct answer in this case. Clear? So is this clear to all of you? So please type in the chat box. Okay, and actually to connect more with these kind of questions and all, you can connect to me with this link, https:/t.me/pw Vinay sir. Okay, so this is the link in Telegram. If you can search over there, you can get the link and you can join this for any discussion with respect to fluid mechanics, thermal heat transfer, applications of thermodynamics, maths questions. Okay, fine. So let us solve this question. The inlet and outlet conditions of a steam for an adiabatic steam turbine, adiabatic steam turbine, are as indicated in the figure. The notations are as usually followed. If the mass flow rate of the steam is 20 kg per second, the power output of the turbine is dash. So they want to calculate the power output of the turbine. They have given you 168 megawatts, 168.785 megawatts. I think these are very close. Okay, now let us see. If we apply the steady flow energy equation, Q dot minus W dot of the control volume is equal to M dot times of delta K dot plus delta P dot plus delta H dot. I think enthalpy values are given, H1, H2 given. Fantastic. So let us see. This is a adiabatic turbine. So this gives you work interaction of the control volume. If you neglect this minus sign, M dot into 1 by 2000, because everything will be in kilowatts, that's why V inlet square minus V outlet square. Normally it is final minus initial, but because of this minus sign I am writing it inverse, plus G by 1000 times of Z in minus Z out plus H in minus H out. You can write this H in minus H out in kilojoule per kg Kelvin now. Okay, because we have written everything in terms of SI units. Clear? So therefore you can see mass flow is 20 kgs, 20 times of 1 by 2000 into velocity in square minus velocity out square. Velocity in is 160, velocity out is 100. So 160 square minus 100 square, that can be written as 60 into 160, correct? Because a square minus b square can be written as a plus b into a minus b. So 100 minus 160 minus 100 is, sorry, this is 160. 160 minus 100 is 60. 160 plus 100 is 260. So this is 260 plus g. So what is the value of g? Nothing is given. So let us take 9.81 because nothing is mentioned here. 9.81 by 1000 times of Z inlet minus Z outlet. So Z in is 10, Z out is 6. So this is 4 plus H inlet minus H outlet. So H in is 3200, H out is 2600. So total 600 kilojoule is the difference. Now if you see this calculation clearly, this couple of zeros and these two zeros gets cancelled. So if you multiply 20 into 6 into 26 by 20, so 20 gets cancelled, 26 times of 6. Okay, and this 20 cancels out this 1000 50 times actually here. Okay, and 4 cancels out this 12.5 times. 9.81 by 12.5 plus 600 into 20, 12,000. So these many kilowatts actually here. Okay, so there is 12,000 kilowatts actually here. So 12,000 kilowatts. So if you convert that to megawatts, this will be somewhere around 12 megawatts, because these terms will be very small actually. So 12 megawatts is what you have, but within this 12, so definitely these two are wrong options, but within this 12 you can see there is certain variation. 157941. Let us compute these values. 26 into 6,
26 into 6, this gives you 6 6 are 36, 3 2 6 are 12, 13 14 15, so 0.156. So 12.156 plus this value 9.81 by 12.5, so 12.156, and this value is actually much small, and this is in kilowatt conversion, so this value will be less than 1 kilowatt. Okay, so if something is less than 1 kilowatt, if you convert that, that will be much very small megawatt actually. Okay, so 12.156 kilowatt is the actual answer in this case. 157 maybe because due to this decimal. Look, understand, this is in kilowatts. Okay, this is also in kilowatts, but this value is less than 1 kilowatt. Understood? So if you convert this to megawatts, it will be like 0.001 megawatt somewhere. Okay, so that's why this 12.156 megawatts is the, this is in megawatts. Okay, because this is in kilowatts actually. So 12.156 megawatts is the actual value of the work generated by the turbine in this case. Clear? So is this clear to all of you? 12.156 megawatts. Okay, that's what you can keep. 12.156 is very close to option A, so that you can tick actually here. Okay, so that's the correct answer. Fine. So yeah, I think then these are the questions. We still have some questions to do, but I think the time is up. So let us see if there is some complicated questions where you cannot do. See, these are the kinds of questions where things are very stagnation properties, all these are very important. Okay, so I have given this, kept these points. So if you see, they're asking you Mach number of the flow. So you know Ts minus T infinity, or basically T at condition 1 is equal to V square by 2 Cp. And since V square Mach number is basically equal to, Mach number is equal to V by A. So if you square this, V square by A square, so V square can be written as A square times of Mach square actually. Okay, so this implies Ts minus T1 initially is equal to acoustic velocity square into Mach square by 2 times of Cp actually is what you have. So they have given you the temperatures, and also gamma value is given. So what will you do with the help of gamma? Look, we can see Ts minus T1. So 360 is the saturation, is the stagnation temperature, and 200 is the normal temperature. So the difference is 160 is equal to this A square can be written as gamma times of R into T1 into Mach square, we don't know the Mach number, divided by 2 times of Cp. So Cp can be written as gamma R times of gamma minus 1 actually. Okay, so this gamma R and this gamma R gets cancelled, this 2 cancels this 100 times actually, and Mach number, this 160 is equal to Mach square times gamma minus 1. So gamma is 1.4, so this is 0.4, so 4 by 10 actually. So 4 cancels this 40 times, so Mach square is equal to 400 actually. Okay, so Mach square is equal to, I think 4, right? Just a minute, this is 1.6 multiplied with this Mach square is 0.4, so 4 by 10, so this gives you 40. So square root of 400 is it? Let us check this calculation. Gamma R times of 200, so gamma RT into Mach square divided by 2 times of Cp. So Cp is gamma R multiplied with gamma minus 1. So this gamma R and gamma R cancels, this is 100 times, so 160 by 100, this 100 is also there here. Okay, so this 100 is also there, so that means this is 4. That's it, because this is going to be 1.60, so this is 0.4. Okay, so if you simplify, Mach square is equal to 4, so Mach is equal to 2. That's it. Okay, 2 is the Mach value, because this 100 is also there. Okay, so this 100 divided with 160 gives you 1.6. So 4, 1.6 if you divide, you will get 0.4. So 0.4 into 10 gives you 4. So Mach square is equal to 4. So Mach number is 2 actually. Okay, so details about ISRO batch. So as we told, from 1st of July, we think I think 1st of July, I think schedule is already launched yesterday by our teammates, one of our friends. Let me check the timetable once. I'll show you. I can't show you, but I will let you know basically. Where is this? Okay, fine, somewhere here. Okay, so around some time back we got the timetable. So I think from 1st of July we are going to start. And coming to the details in this class, like I have to search a lot of messages. It is there somewhere. Okay, so hopefully it is around for some 60 days. That's what we know. I think launch has already happened some couple of days back. And some of our team members has joined. So each teacher ESC batch in which month it will be started, that is in the plan. Again, we have to fix a date for that, but right now we are focusing on this ISRO test series and all these things. Little details about this ISRO batch. Like in ISRO batch, normally the things happen in this way. बेसिकली हम थियरी भी कवर करते हैं बहुत केस में, लाइक नॉट ऑफ थियरी बट वेरी लेस, खुद थोड़ा थोड़ा इंपॉर्टेंट पॉइंट्स टच करके. ओके, एंड वी विल सॉल्व मोस्टली क्वेश्चंस, सम न्यू क्वेश्चंस एंड आल्सो दिस some important PYQs which were not solved in this YouTube sessions and all. We will definitely solve there, because it's quite possible that in 2 hours time we cannot complete all the PYQs. You have some 50 to 60 PYQs, so we cannot clear all those things. So इसलिए हम बहुत सारे PYQs यहाँ सॉल्व करने की कोशिश करते हैं, एंड अगर यहाँ नहीं हुआ तो उस ISRO की PYQ उस ISRO बैच में हम सॉल्व करते हैं, एंड उस PYQs के साथ हम कुछ नए क्वेश्चंस भी डिस्कस करते हैं, एंड ऑल्सो जो इंपॉर्टेंट थियरी पॉइंट्स होते हैं वो पॉइंट्स भी हम थोड़ा ध्यान देते हैं उस बैच पे. ओके, सो this ISRO batch is more like a bit of case theory and also some PYQ plus some new questions, things like this. Okay, so in this batch I have kept some slides which are very important for ISRO exam, क्योंकि हर बार ISRO का एग्जाम होता है, डेफिनेटली ये टॉपिक से क्वेश्चंस आते हैं हमको. ठीक है, सो इसलिए हम कुछ पॉइंट्स, अच्छा पॉइंट्स एंड थोड़ा लाइक basically some objective type of questions है, सब चीज मैंने डाला था. So please go through this PPT once, and I think some important questions are there. Some normal questions you can solve that actually using your fluid, normally some simple applications of thermodynamics knowledge, and also this hydraulic testing of boilers. As we told, normally this is called HT in industrial terms. Any device wherever if you want to do hydro testing, normally this is called hydro testing. HT is called hydro test. So when you do HT, every time whatever is the operating pressure of that particular device, it can be boiler, turbine, whatever, you test the device at around 1.5 to 2 times of that pressure. Okay, so this is generally the correct answer, at 1.5 to 2 times the working pressure. Okay, so working pressure is basically whenever that equipment is in working condition, whatever the pressure that is dealt by the device, whenever if there is some leak or something at any device, you actually maintain that device. Means basically you will do the necessary modification in the device, and also you will test it before going for operation. Okay, so during testing, doing hydro testing, especially hydro test is basically something like you fill the device with water at a pressure which is around 1.5 to 2 times. Normally 1.8 is the ratio, we maintain 1.8, 1.9 sometimes. Okay, so that pressure will maintain the vessel, we will fill the water at that pressure, and we will hold the device for some time. Okay, so when we hold the device, then when you do this hydro test, then it is done around at 1.5 to 2 times the work pressure generally. Okay, will the Titanic also tested, sir? Titanic was tested, that was blasted previously. Okay, so maybe somewhere there could be some design faults or somewhere that could happen. Yes, because but that's destiny, guys. I'm telling you, if there is a destiny for you to die here, you will buy a ticket with 2 crore rupees, you will go under the sea at that time of your death, and you will die. That's called destiny. Okay, but at the same time, a lot of hard work is needed, buying the ticket and all, going there, effort, a lot of effort is needed, but please put your efforts. Preparation is a process. Okay, I'm telling you about this, and take every opportunity that you get very seriously. Okay, don't feel like, okay, my age is 24 or 23, so if I leave ISRO now, again next year after 2 years there'll be recruitment, so I'll get posted. Don't think of this, because last year before this recruitment, ISRO has announced vacancies, mechanical 165 vacancies around, you got. Before this announcement came in now, 2019. Okay, and exam got commenced in January 2020. Okay, at that time age limit was 35. People who missed that at January 2020, by the time January 2020 there was no COVID effective in India. Okay, so they expected that next recruitment is going to come in around 2021 or 2022, so I will be available for that exam. Okay, but you can see for 4 years, 2019 to this day, 2023 June almost. Okay, there is no recruitment by ISRO for this bulk recruitment, and also try to understand, they have decreased the age limit from 35 to 28. So let us think of a person who is at 25 at that time, thinking that he will get an opportunity in 1-2 years. Now who is in 25 at that time, he is not eligible for the exam now. Okay, so use every opportunity, and if you have any doubts regarding anything, as I told you, you can contact me, means basically in Telegram. This is the PW group, associated group actually, so you can reach me there for any doubts regarding the thermal subjects, basically thermofluid, heat transfer, applications of thermodynamics, these things, and also maths, of course. Okay, so you can contact me here. Okay, so we will close this session because we have done a bit of quick things in this session. So did you all enjoy this session, like this session, questions and all? Liking means I don't mean the hitting the like button, but conceptually. Okay, did you all like the session, and did you all basically learn some new points actually in solving calculations, questions, everything? Okay, fine then. So thank you all. We'll meet sometime again later. Thank you for the extra information. Great, hugs bunny. So again we'll meet sometime. At some point we'll meet again and we will discuss some more things. Okay, so thank you guys. Bye all of you. Take care. Okay, so good night. I wish you all the best for your ISRO exam, and if possible, anyway, the batch, I think the ISO batch fees will also be not much. I don't know what is the fees they are taking, but it won't be much as per my idea. So if possible, you can, if you have some time, get enrolled and boost your preparation. Okay, fine then. Thank you all. Okay, if you have any doubts, you can speak to me, or else it's fine. Okay, so thank you all. Bye, take care then. I think no more doubts. Thank you all. Good night, take care. Bye all of you. Signing off.